It's lovely to have you here. Tonight we're going to explore the invisible universe and discover just how little of the cosmos our eyes are actually able to see. Just a little favour to ask before we begin. As I'm sure most of you know, there are no ads on these videos, so nothing will distract you tonight. If you have a moment to spare, I'd really appreciate it if you took a look at our ebook over on the Sleepy Scientist website. It takes the ideas from these videos and gives them room on the page, unhurried, laid out with all the space they need to properly settle in the mind. The whole thing is narrated too, so you can read it, or simply listen. And at the close of each movement there's a short quiz waiting, a gentle way to see what stayed with you and to turn the ideas over once more before moving on. The QR code is up on screen, and there's a link in the description to the sleepyscientist.com whenever you're ready. Every reader who takes a look is the reason these videos keep appearing, and to anyone who takes the time to buy it, I don't think you quite understand how much that means. That's the only ask tonight, and thank you sincerely. Now, before we begin, let me know where in the world you're listening from and what time it is for you. I always enjoy seeing these little check-ins from around the world as people settle in for the night or the morning or somewhere quietly in between. The familiar night sky is only a narrow glimpse of everything travelling through space. Beyond visible light, the universe is filled with radio waves, microwaves, infrared radiation, ultraviolet light, X-rays and gamma rays. There are also neutrinos passing almost unnoticed through entire planets, gravitational waves gently stretching space-time, and dark matter revealing itself only through the pull of its gravity. Together these hidden signals allow astronomers to study cold gas between the stars, warm dust inside stellar nurseries, violent activity around black holes, the oldest light in the universe and some of the most energetic events ever observed. So settle in, get comfortable, and let us slowly look beyond the limits of human sight into the vast and quietly active universe that has been there all along. Look up at the night sky, and it can seem as though the universe has presented itself quite openly. Stars shine. Planets reflect sunlight. The moon displays its familiar craters and plains. On a clear night, even the pale band of the Milky Way may stretch overhead. Yet almost everything visible to the human eye represents only a narrow portion of the information moving through space. Human vision detects visible light, a small region of the electromagnetic spectrum with wavelengths roughly between 400 and 700 nanometers. A nanometer is 1/1000th of a meter, so these waves are extraordinarily small. Even so, visible light sits somewhere near the middle of a far larger family. Beyond the red end of human vision lie infrared radiation, microwaves and radio waves. Beyond violet lie ultraviolet radiation, X-rays and gamma rays. Radio wavelengths can be longer than buildings, while the shortest gamma rays can be smaller than atomic nuclei. Together they form the electromagnetic spectrum. Imagine the entire spectrum as an immensely long musical keyboard. Human eyes would hear only a few neighbouring notes. We have become so familiar with those notes that they feel like the whole melody, but the universe has been playing across the entire instrument. A bright visible object is not necessarily a fully understood object. The sun appears as a calm yellow-white disk, but ultraviolet and X-ray observations reveal violent activity in its outer atmosphere. A seemingly dark cloud between the stars may glow in infrared light because it contains warm dust. A quiet-looking galaxy may produce powerful radio jets extending far beyond its visible stars. Different wavelengths reveal different physical conditions because radiation is produced and absorbed through different mechanisms. Cold clouds of hydrogen can emit radio waves. Slightly warmer interstellar dust radiates strongly in the infrared. Extremely hot gas surrounding black holes or filling galaxy clusters shines in X-rays. Nuclear reactions and collisions between very energetic particles can produce gamma rays. Magnetic fields can influence charged particles and create distinctive radio emission or polarization patterns. No single band of light provides the complete story. Earth's atmosphere also decides which portions of the universe can reach instruments on the ground. Visible light passes through the atmosphere reasonably well, which is convenient for both astronomers and anyone hoping not to walk into a tree at night. Many radio wavelengths also reach the surface, allowing enormous radio observatories to operate on Earth. Other wavelengths are partly or almost entirely blocked. Water vapour and other atmospheric gases absorb much infrared radiation. Ozone and molecular oxygen absorb most ultraviolet light. X-rays and gamma rays are stopped high above the ground. This protection is extremely useful for life, because energetic radiation can damage biological tissue. It is slightly less convenient for astronomers. To observe these hidden regions, instruments must sometimes be carried above much of the atmosphere by high-altitude balloons or specialized aircraft. In many cases, telescopes must be placed in orbit or sent farther into space. Organizations including the National Aeronautics and Space Administration, the European Space Agency, the European Southern Observatory, and the National Radio Astronomy Observatory operate or support instruments designed for these different observing environments. Their work is joined by universities, national laboratories, and international collaborations involving thousands of scientists, engineers, and data specialists. Invisible astronomy is not limited to invisible light. Cosmic rays are high-energy particles, mostly atomic nuclei, that arrive from the Sun, the Milky Way, and more distant sources. Neutrinos are extremely elusive particles that can pass through stars, planets, and human bodies with very little chance of interacting. Gravitational waves are ripples in space-time produced by accelerating masses, particularly events such as the collision of black holes or neutron stars. These signals are fundamentally different from electromagnetic radiation. A neutrino is not a type of light. A gravitational wave is not a hidden colour. Each is a separate messenger carrying information through the universe in its own way. This leads to multi-messenger astronomy. When several kinds of signal are detected from the same event, they can be combined into a more complete physical account. Light may reveal temperature and chemical composition. Neutrinos may carry information from dense interiors that light cannot escape. Gravitational waves may reveal the motion and masses of compact objects. Cosmic particles may expose powerful natural accelerators. Each messenger answers different questions, and together they reduce the chances of mistaking one clue for the entire event. The invisible universe is therefore not a second cosmos concealed behind the one we know. It is the same universe, examined through information that human biology was never designed to detect directly. Our eyes evolved to function beneath the light of one nearby star and within the atmosphere of one small planet. They were not built to map cold hydrogen between spiral arms, measure million-degree plasma, or detect the trembling of space-time. Scientific instruments extend that limited biological window. They translate radio waves, infrared radiation, energetic photons, particles and gravitational distortions into signals we can measure and images we can understand. The familiar stars remain where they have always been. Nothing needs to be removed from the visible sky. Instead, the darkness around them gradually fills with structure, energy, and motion. What looked empty was never truly empty. We were simply listening to only a few notes. For much of human history, astronomy was mainly the careful study of where objects appeared in the sky and how they moved. Astronomers tracked the paths of the sun, moon, and planets. They recorded eclipses, measured the positions of stars and developed increasingly accurate models of celestial motion. These observations were enormously valuable, but they said relatively little about what distant objects were physically made from. A star could be mapped with great precision, while its composition remained almost entirely mysterious. That began to change when light itself became an object of scientific investigation. During the 17th century, Isaac Newton carried out a series of experiments using sunlight and glass prisms. When a narrow beam of white light passed through a prism, it spread into a band of colours running from red through orange, yellow, green and blue to violet. This effect was already familiar, but Newton investigated it more carefully. He showed that the prism was not simply adding colours to white light. The colours were already present within the light and were being separated because each colour was refracted by a slightly different amount. Newton referred to the coloured band as a spectrum. By passing one selected colour through a second prism, he showed that it did not split into a new range of colours. By recombining the separated colours, he could produce white light again. White light was therefore not a simple, colourless substance, it was a mixture. The spectrum soon proved to extend beyond the portion visible to human eyes. In 1800, William Herschel investigated the heating effects of different colours in sunlight. He placed thermometers at various positions across a spectrum created by a prism and found that the measured temperature increased towards the red end. Herschel then placed a thermometer just beyond the visible red light, in a region that appeared dark. The temperature rose even higher. Something invisible was carrying energy. This radiation became known as infrared, meaning beyond red. Herschel had shown that the sun emitted a form of light that human eyes could not see, but that matter could detect through heating. Only 1 year later, Johann Wilhelm Ritter explored the opposite end of the spectrum. Ritter knew that violet light caused certain chemical reactions more strongly than red light. He exposed silver chloride to different parts of a spectrum and observed how quickly the substance darkened. The reaction became stronger towards the violet end. When Ritter placed silver chloride beyond the visible violet light, it darkened even more rapidly. Another invisible region had been discovered. This radiation was later called ultraviolet, meaning beyond violet. Infrared had revealed itself through heat, while ultraviolet had revealed itself through chemistry. The human eye detected neither, yet both were clearly real. During the 19th century, James Clerk Maxwell brought electricity, magnetism and light into a single theoretical framework. Maxwell's equations showed that changing electric fields produce magnetic fields, and that changing magnetic fields produce electric fields. Together, these linked disturbances could travel through space as waves. The speed predicted for these electromagnetic waves matched the measured speed of light. The conclusion was remarkable. Visible light was an electromagnetic wave. Electricity, magnetism and light were not unrelated subjects, but different expressions of one physical system. Maxwell's theory also predicted electromagnetic waves with wavelengths far beyond those of visible light. In the late 19th century, Heinrich Hertz produced and detected radio waves in the laboratory. He created rapidly changing electrical currents that generated electromagnetic waves, then detected those waves across a short distance using a separate circuit. Hertz confirmed that the waves could be reflected, refracted and made to interfere, much like visible light. Maxwell's invisible waves were no longer only a mathematical prediction. All electromagnetic radiation can be described using wavelength and frequency. Wavelength is the distance between repeating points in a wave. Frequency is the number of wave cycles passing a location during a given time. The relationship can be stated simply. The speed of light equals wavelength multiplied by frequency. Because the speed of light in a vacuum is constant, a longer wavelength corresponds to a lower frequency. A shorter wavelength corresponds to a higher frequency. Later quantum theory added another important connection. Electromagnetic radiation can also be described as particles called photons. Photon energy increases with frequency, so shorter wavelength radiation generally carries more energy per photon. Radio waves have long wavelengths, low frequencies, and relatively low photon energies. Gamma rays occupy the opposite extreme, with very short wavelengths, very high frequencies, and highly energetic photons. The electromagnetic spectrum is continuous. There are no physical walls where radio suddenly becomes microwave or ultraviolet suddenly becomes X-ray. These names are useful scientific categories, often based on wavelength, energy, detection method, or typical source. They help organize the spectrum, but nature does not pause to consult the labels. Another major transformation came through spectroscopy, the separation and measurement of light according to wavelength. In the early 19th century, Joseph von Fraunhofer examined the solar spectrum in detail and recorded hundreds of narrow dark lines crossing its colours. These became known as Fraunhofer lines. Their meaning was not understood immediately. Several decades later, Gustav Kirchhoff and Robert Bunsen studied the light produced by heated chemical elements. They found that each element created a distinctive pattern of bright spectral lines at particular wavelengths. Kirchhoff recognized that the dark lines in sunlight occurred at the same wavelengths as the bright lines produced by known elements in the laboratory. Atoms in the sun's cooler outer layers were absorbing specific wavelengths from the hotter light beneath them. The solar spectrum therefore contained a chemical fingerprint. For the first time, astronomers could determine what a distant star was made from, without travelling anywhere near it. Spectral lines could also reveal temperature, density, and ionization. Shifts in wavelength could expose motion through the Doppler effect. Splitting or broadening of lines could provide information about magnetic fields, pressure, and rotation. Light had become more than illumination. It was a messenger carrying evidence about matter and energy across enormous distances. Every part of the electromagnetic spectrum carries its own physical clues. Radio waves, infrared radiation, ultraviolet light, X-rays and gamma rays are not merely invisible colours. They reveal different temperatures, particles, environments and mechanisms. The universe had always been sending these messages. Science gradually learned how to separate them, measure them, and begin to understand what they were saying. Radio waves occupy the longest wavelength region commonly used in astronomy. Depending on exactly where the boundaries are drawn, they can range from wavelengths of a few millimeters to many kilometers. That broad range makes radio astronomy less like a single narrow window, and more like an entire corridor of different possibilities. Some radio waves reveal cold clouds of gas. Others trace magnetic fields, energetic particles, stellar explosions, or enormous jets launched from the centres of galaxies. Much of this activity is faint or completely invisible in ordinary light, yet it can dominate the sky when observed at radio wavelengths. The radio universe was discovered almost by accident. In the early 1930s, the American engineer Carl Jansky was working for Bell Telephone Laboratories. His task was to investigate sources of radio interference that might disrupt transatlantic telephone communication. Jansky built a large rotating antenna designed to identify where unwanted radio noise was coming from. The structure could turn on wheels and was sometimes compared to a merry-go-round, although presumably it offered a rather disappointing ride. He identified several familiar sources of interference, including nearby thunderstorms and more distant storms. But another signal remained. This faint hiss rose and fell with a regular period of approximately 23 hours and 56 minutes. That timing matched a sidereal day, the period of Earth's rotation relative to the distant stars rather than the Sun. Jansky realized that the signal was coming from space. More specifically, it appeared strongest in the direction of the centre of the Milky Way, in the constellation Sagittarius. The galaxy was producing radio waves. Jansky had opened an entirely new branch of astronomy, although his discovery did not immediately lead to a large program of professional radio observatories. Much of the early progress came instead from Grota Rieber, an amateur radio operator and engineer. In the late 1930s, Rieber built a purpose-designed radio telescope in the garden of his home in Illinois. Its parabolic dish was roughly 9 meters across. The dish collected incoming radio waves and focused them onto a receiver, using the same basic geometry that allows an optical telescope mirror to collect visible light. Rieber systematically scanned the sky and created one of the first radio maps of the Milky Way. His work confirmed Jansky's discovery and showed that radio emission was distributed across broad regions of the galaxy rather than coming from only one isolated point. Radio telescopes often need to be large because their wavelengths are much longer than visible wavelengths. A telescope's ability to separate fine details is called angular resolution. For a single circular aperture, the resolution depends mainly on the wavelength being observed and the diameter of the telescope. Longer wavelengths produce poorer resolution unless the collecting aperture is made larger. Visible light telescopes can distinguish fine details with mirrors a few meters across because visible wavelengths are extremely short. A radio telescope observing waves measured in centimeters or meters may require a dish tens or hundreds of meters wide to achieve a useful view. Building ever larger dishes eventually becomes difficult. Structures sag under their own weight, winds push against them, and engineering costs become rather enthusiastic. Radio astronomers therefore developed interferometry. In radio interferometry, 2 or more separated antennas observe the same source at the same time. Their signals are combined with extremely precise timing. Differences in the arrival of the wave at each antenna contain information about the direction and structure of the source. A network of dishes can behave in important respects like a telescope with a diameter comparable to the greatest separation between its antennas. This separation is called the baseline. The Carl G. Jansky Very Large Array in New Mexico uses 27 movable antennas arranged along 3 long arms. By changing the spacing between the dishes, astronomers can adjust the instrument for different combinations of sensitivity and resolution. The Atacama Large Millimeter/Sub-Millimeter Array operates high in the Atacama Desert of northern Chile. It observes relatively short radio wavelengths, close to the boundary between radio and infrared, where coal dust and molecules produce rich astronomical signals. Its high-altitude location reduces interference from water vapor in Earth's atmosphere, which absorbs many millimeter and sub-millimeter wavelengths. The Square Kilometre Array Observatory is being developed through sites in Australia and South Africa. It is designed to combine enormous numbers of antennas into one of the most sensitive radio facilities ever constructed. An even more extended technique is called very long baseline interferometry. Here, radio telescopes separated by entire continents observe together. Their recordings are synchronized using highly accurate atomic clocks and later combined. The effective aperture can approach the diameter of Earth. On rare occasions, antennas in space have been added, creating baselines even larger than the planet. This technique can achieve astonishingly fine angular resolution, allowing astronomers to examine compact regions near black holes, map distant quasars, and measure the motions of objects across the galaxy. Many of the most dramatic radio sources shine through synchrotron radiation. This occurs when electrically charged particles, usually electrons moving at speeds close to the speed of light, spiral through magnetic fields. As their direction changes, they accelerate and release electromagnetic radiation. Synchrotron emission often covers a broad range of radio frequencies and is naturally polarized. That polarization can help reveal the direction and organization of magnetic fields. Supernova remnants glow strongly through synchrotron radiation because their expanding shock waves accelerate particles and compress surrounding magnetic fields. Radio galaxies and quasars can also be spectacular synchrotron sources. At the center of these systems lies an active galactic nucleus powered by matter, falling towards a supermassive black hole. Some of the surrounding energy is channeled into narrow relativistic jets. These jets can travel thousands or even millions of light years into intergalactic space. They may end in vast radio-emitting lobes that extend far beyond the visible galaxy. The black hole itself is not sending material outward from inside its event horizon. The jets are launched from the hot, magnetized environment outside the horizon, where the accretion disk and rotating magnetic fields redirect part of the infalling energy. Radio astronomy also reveals much colder and quieter material. Neutral hydrogen atoms can produce radiation with a wavelength of approximately 21 centimeters. This emission comes from a subtle change in the relative orientation of the proton and electron spins within the atom. When their magnetic relationship shifts from a slightly higher energy state to a lower energy state, a radio photon is released. An individual hydrogen atom undergoes this transition extremely rarely. Space, however, contains an impressive number of hydrogen atoms, so their combined emission can be readily detected. Visible light from distant parts of the Milky Way is often blocked by interstellar dust. 21 centimeter radio waves pass through much of that dust, allowing astronomers to map neutral hydrogen across the galaxy. The wavelength is also shifted by the Doppler effect when gas moves towards or away from Earth. By measuring these shifts, astronomers can estimate the motion of hydrogen in different directions. These observations help to reveal the Milky Way's spiral structure and its pattern of rotation, including regions hidden on the far side of dense dust clouds. Some radio signals arrive not as a steady glow but as remarkably regular pulses. Pulsars were discovered in 1967 by Jocelyn Bell Burnell while she was analysing data from a radio telescope constructed by a research group led by Anthony Hewish. Bell Burnell noticed a signal repeating with extraordinary precision. After instrumental faults and human interference were ruled out, the pulses were recognised as coming from a new kind of astronomical object. A pulsar is a rapidly rotating neutron star. Its magnetic field directs beams of radiation away from magnetic poles that are often misaligned with the rotation axis. As the neutron star turns, a beam may sweep across Earth like the beam from a lighthouse. Each sweep produces a pulse. Some pulsars rotate only a few times each second. Others, known as millisecond pulsars, rotate hundreds of times per second. Their regularity makes them exceptionally precise cosmic clocks. Tiny variations in pulse arrival times can reveal planets orbiting pulsars, changes in the interstellar plasma, and the effects of motion through a gravitational field. Pulsars in binary systems have also provided powerful tests of general relativity. Networks of carefully timed millisecond pulsars are now used to search for very low-frequency gravitational waves, particularly those expected from populations of orbiting supermassive black hole pairs. The radio sky therefore reveals both the quiet architecture and the hidden violence of space. It maps cold hydrogen between stars, traces magnetic fields through polarized emission, identifies compact neutron stars, and exposes jets larger than entire galaxies. To human eyes, much of this structure is completely dark. At radio wavelengths, the darkness is filled with signals. Microwaves occupy the short wavelength end of the radio spectrum. Their wavelengths are generally shorter than those used for many traditional radio observations, but longer than infrared light. This region is especially useful because it carries information from very cold material, from planetary atmospheres, and most remarkably from the early universe itself. Molecules in cold clouds can emit and absorb microwave radiation at precise wavelengths. By measuring those spectral lines, astronomers can identify substances drifting through interstellar space and estimate the temperature, density, and motion of the gas. Microwaves also reveal features in planetary atmospheres that may be hidden beneath clouds at visible wavelengths. They can trace temperature patterns, chemical composition, and deeper atmospheric layers that ordinary light cannot reach easily. Yet the most famous microwave signal in astronomy does not come from a planet, a cloud, or even a galaxy. It comes from almost everywhere. The cosmic microwave background is relic radiation from a time when the universe was only about 380,000 years old. Today, that age may sound impressively ancient, but compared with the present age of the universe, it belongs to cosmic infancy. There were no stars, no planets, and no galaxies. Matter existed mainly as hydrogen and helium nuclei, free electrons and radiation. The early universe was hot, dense, and opaque. Photons moved constantly, but they could not travel very far before scattering from free electrons. The situation was somewhat like trying to see through a brilliantly illuminated fog. Light was everywhere, but it could not move freely across large distances. As the universe expanded, it cooled. Eventually, the temperature fell to a few thousand Kelvin, allowing free electrons to combine with atomic nuclei. Hydrogen nuclei, consisting of single protons, captured electrons and formed neutral hydrogen atoms. Helium nuclei did the same through related stages. This period is called recombination, although the name is slightly misleading because the electrons and nuclei were combining for the first time rather than reuniting after an earlier separation. Once most free electrons had been captured into neutral atoms, photons were far less likely to scatter. The cosmic fog cleared. Radiation could then travel enormous distances through space. The light released from that era is still moving through the universe today. However, it no longer has the same wavelength or temperature that it had when it began its journey. Cosmic expansion stretches the wavelengths of travelling radiation. As space expands, the light crossing it is redshifted towards longer wavelengths. Radiation that once had the spectral character of a hot glowing plasma has therefore been stretched into the microwave region. Today, the cosmic microwave background has a temperature of approximately 2.7 Kelvin, only a few degrees above absolute zero. It fills the sky in every direction. The signal was detected unexpectedly in the 1960s by Arno Penzias and Robert Wilson, two researchers working at Bell Telephone Laboratories. They were using a large horn-shaped radio antenna in New Jersey to study microwave signals. Their observations contained a persistent background noise that appeared regardless of where the antenna was pointed. The signal did not behave like interference from a city, a nearby radio source, or a particular region of the Milky Way. It arrived from all directions. Penzias and Wilson carefully investigated possible causes. They checked their equipment, considered atmospheric effects, and removed a layer of material deposited inside the antenna by pigeons. The noise remained. At nearby Princeton University, a group led by Robert Dick was preparing an experiment to search for relic radiation from the early universe. When the two groups learned of each other's work, the explanation became clear. Penzias and Wilson had detected the cosmic microwave background. Their discovery was announced in 1965. The idea that the early universe might leave behind a cooling field of radiation had been explored earlier. George Gamow, Ralph Alpher, and Robert Herman were among the scientists associated with theoretical work on the hot early universe and its possible thermal remnant. The historical development was not a single neat prediction, followed by one tidy confirmation. Several researchers contributed ideas, calculations, and later interpretations. As often happens in science, the path looks straighter in a textbook than it did while people were actually walking along it. The discovery of the cosmic microwave background became one of the strongest pieces of evidence for the hot Big Bang model. Later observations measured the signal with far greater precision. The National Aeronautics and Space Administration launched the Cosmic Background Explorer mission in 1989. One of its instruments measured the spectrum of the cosmic microwave background. The result matched an almost perfect blackbody spectrum. A blackbody is an idealized object that absorbs and emits radiation according to its temperature. The shape of the measured spectrum was extraordinarily close to the theoretical form expected for radiation that had once been in thermal equilibrium. This was an important result. It showed that the cosmic microwave background was not simply a collection of unrelated microwave sources. It carried the thermal signature of the early universe. Another instrument aboard the Cosmic Background Explorer detected tiny variations in temperature across the sky. The background was extremely uniform, but not perfectly so. These small differences became known as anisotropies. They were typically only tens to hundreds of millionths of a degree. That is an astonishingly slight contrast. If the average cosmic microwave background temperature were represented by a room temperature surface, the fluctuations would be far smaller than the changes created by a gentle breath. Yet these differences mattered enormously. They represented tiny variations in density in the young universe. Regions that were slightly denser than average exerted a little more gravitational attraction. Over billions of years, gravity amplified those small differences. Matter gathered into larger concentrations. The earlier stars formed, galaxies emerged, clusters and immense filaments gradually developed. The structure of the modern universe grew from extremely subtle irregularities. The Wilkinson Microwave Anisotropy Probe, launched by the National Aeronautics and Space Administration in 2001, mapped these temperature variations across the full sky with much greater precision. The European Space Agency's Planck mission later produced even more detailed maps. These observations revealed a distinctive pattern of fluctuations across different angular scales. That pattern was shaped by acoustic oscillations in the early universe. Before recombination, ordinary matter and radiation formed a tightly coupled plasma. Gravity pulled matter towards slightly denser regions. As material compressed, radiation pressure pushed back. The result was a series of compressions and expansions, rather like sound waves moving through the early plasma. These were not sound waves travelling through air. They were pressure waves in a hot mixture of particles and radiation. When recombination occurred, the pattern was effectively frozen into the cosmic microwave background. The measured sizes and strengths of these fluctuations contain information about the contents and geometry of the universe. They help constrain the proportion of ordinary matter, dark matter, and dark energy. They provide evidence that space is very close to geometrically flat on large scales. They also help estimate the age of the universe and the rate at which it has expanded. Within the standard lambda cold dark matter model, the cosmic microwave background acts as one of the most important sources of cosmological evidence. The name refers to a model containing a cosmological constant, represented by the word lambda, and cold dark matter, meaning dark matter that was moving slowly compared with light when cosmic structure began to form. Extracting this information is not simple, because the Milky Way also produces microwave radiation. Warm dust emits at microwave and submillimeter wavelengths. Free electrons create radiation as they are accelerated by nearby ions. Charged particles spiraling through galactic magnetic fields produce synchrotron emission. These foregrounds can be much brighter than the faint cosmological variations underneath them. Astronomers therefore compare observations across many frequencies. Different sources have different spectral signatures, allowing the galactic foregrounds to be modelled and separated from the cosmic signal. It is a delicate process. The oldest light in the universe arrives through a foreground supplied by our own galaxy, which is rather like trying to study a quiet conversation while standing behind a mildly enthusiastic orchestra. The cosmic microwave background is also polarized. Polarization describes the preferred orientation of electromagnetic waves. Scattering in the early universe produced a subtle polarization pattern across the sky. The most clearly measured form is commonly called even pattern polarization. It records information about density variations and the motion of the early plasma. A second form, often called odd pattern polarization, is much harder to detect. Some odd pattern polarization is produced when gravitational lensing bends and distorts the background radiation during its journey through the universe. A primordial version could also have been created by gravitational waves in the extremely early universe, possibly connected with cosmic inflation. Detecting that primordial signal would provide extraordinary evidence about conditions at energies far beyond those accessible in laboratories. The search remains difficult because the expected pattern is faint, and because foreground emission from the Milky Way can imitate or obscure parts of it. Microwave astronomy therefore reaches both outward and backward. It studies cold molecules, planetary atmospheres and structures within the Milky Way. At the same time, it carries observation to an age before stars had begun to shine. The cosmic microwave background is not light from the first stars. It is older than every star. It is the cooled afterglow of the moment when the universe first became transparent, still crossing space after more than 13 billion years. Beyond the red edge of human vision lies infrared radiation, a broad region of the electromagnetic spectrum with wavelengths longer than visible light but shorter than microwaves. Infrared itself covers an enormous range. Near-infrared wavelengths sit close to visible red light, while mid-infrared and far-infrared wavelengths extend towards the microwave region. Because of this wide span, infrared astronomy can reveal many different physical processes rather than simply producing one universal view of heat. All matter above absolute zero emits electromagnetic radiation. Absolute zero is the lowest possible temperature, where thermal motion reaches its minimum. Any object warmer than this possesses thermal energy, and releases some of that energy as radiation. The temperature of an object strongly affects the wavelengths at which it emits most intensely. Very hot objects can glow visibly. Cooler objects tend to radiate most strongly at longer wavelengths, often in the infrared. A person, for example, emits infrared radiation because the human body is warm. So does a planet, a cloud of dust, and the telescope attempting to observe them. This does not mean that every infrared image is a simple heat map. Near-infrared telescopes can detect reflected starlight, emission from atoms and molecules, and light from stars whose surfaces are cooler than those shining most strongly at visible wavelengths. At longer infrared wavelengths, thermal emission from warm or cool material becomes increasingly important. The exact meaning of an infrared observation therefore depends on the wavelength being measured and the physical source producing the radiation. Interstellar dust is one of the most important sources in the infrared universe. Dust grains are tiny solid particles made from materials such as silicates, carbon-rich compounds and frozen substances. They are scattered through the spaces between stars, often mixed with large clouds of gas. These grains absorb visible and ultraviolet radiation from nearby stars. The absorbed energy warms the dust slightly, after which it is re-radiated at longer infrared wavelengths. A cloud that appears completely black in visible light may therefore glow brightly in the infrared. Infrared radiation can also pass through dusty regions more easily than visible light. In general, longer wavelengths are scattered and absorbed less strongly by small dust grains, although the amount of penetration depends on the exact wavelength and composition of the material. This makes infrared astronomy especially useful for studying stellar nurseries. Stars form inside cold, dense molecular clouds where gas and dust collapse under gravity. The youngest stars are often wrapped in thick cocoons that hide them from visible telescopes. The Orion molecular cloud is one of the nearest and most extensively studied regions of active star formation. Visible images reveal bright glowing gas and dark lanes of dust, but infrared observations uncover many young stars buried inside the cloud. They also reveal disks of material surrounding newborn stars, jets driven outward from young stellar systems, and knots of gas heated by shocks. Infrared astronomy can therefore look into regions where stars are still assembling, long before their surroundings have cleared enough for visible light to escape freely. The history of infrared astronomy begins with William Herschel, who discovered infrared radiation in 1800 by measuring a heating effect beyond the red end of the visible spectrum. That discovery should not be confused with the Herschel Space Observatory, a much later mission named in his honour. The Herschel Space Observatory was operated by the European Space Agency and launched in 2009. It observed far-infrared and sub-millimeter wavelengths, studying cold dust, star-forming clouds, distant galaxies, and the chemical composition of space. Several other observatories helped transform infrared astronomy. The Infrared Astronomical Satellite, launched in 1983, carried out the first infrared survey of nearly the entire sky from space. It discovered large numbers of previously unknown infrared sources and revealed widespread dust emission across the Milky Way. The Spitzer Space Telescope, launched by the National Aeronautics and Space Administration in 2003, studied everything from nearby asteroids to distant galaxies. Its instruments examined cool stars, dusty stellar nurseries, protoplanetary disks, and the infrared glow of galaxies billions of light-years away. Infrared observatories often need to be cooled. A warm telescope emits infrared radiation of its own. If that radiation reaches the detectors, the observatory can partly obscure the faint cosmic signals it is trying to measure. It is rather like attempting to listen for a whisper while the microphone is quietly humming to itself. Some instruments use cryogenic cooling systems. Others rely on passive cooling by placing the telescope behind a sun shield and allowing heat to radiate away into space. The James Webb Space Telescope uses both careful engineering and its location to remain cold. Its primary mirror is made from 18 hexagonal segments that operate together as one large reflecting surface. The mirror spans roughly 6.5 meters and is coated with a thin layer of gold, which reflects infrared radiation efficiently. A large multi-layer sun shield separates the telescope from the Sun, Earth and Moon. This allows the mirrors and instruments on the cold side to remain at very low temperatures. The observatory operates near the second Sun-Earth Lagrange point, roughly 1.5 million kilometers from Earth. At this location, the telescope travels around the Sun while remaining broadly aligned with Earth. The Sun, Earth and Moon stay on the same side of the sun shield, helping maintain a stable thermal environment. Near-infrared and mid-infrared observations allow the James Webb Space Telescope and other facilities to study a remarkable range of objects. Cool stars emit a larger share of their energy in the infrared than hotter stars do. Brown dwarfs, which are less massive than true stars and cannot sustain ordinary hydrogen fusion in their cores, can also be easier to detect at infrared wavelengths. Protoplanetary disks glow as their dust absorbs energy from young stars. Their infrared spectra can reveal dust temperatures, grain properties, and molecular ingredients involved in planet formation. Infrared observations are also useful for examining exoplanet atmospheres. When a planet passes in front of its star, some starlight may filter through the planet's atmosphere before reaching a telescope. Molecules in the atmosphere can absorb particular wavelengths, leaving patterns in the measured spectrum. Water vapour, carbon dioxide and methane each have characteristic infrared features. Similar molecules can also be investigated through thermal emission from the planet or through changes measured as the planet moves behind its star. Detecting one of these substances does not automatically demonstrate the presence of life. Water vapour can arise naturally in lifeless atmospheres. Carbon dioxide may be produced by volcanic activity. Methane can have biological sources, but it can also form through geological and chemical processes. A possible biological interpretation must be tested against the planet's temperature, atmospheric pressure, geology, radiation environment, and the behaviour of its host star. Infrared light also allows astronomers to study the distant universe. As the universe expands, travelling light is stretched to longer wavelengths. This process is called cosmological redshift. Ultraviolet or visible light emitted by a very distant early galaxy may be shifted into the infrared by the time it reaches Earth. The farther the light has travelled through expanding space, the greater this stretching can become. Infrared telescopes can therefore observe ancient galaxies whose original light has moved entirely beyond the visible range. The same region of the spectrum reveals young stars hidden inside nearby dust clouds, and early galaxies shining across most of cosmic history. Infrared astronomy connects the cold, obscured birthplaces of stars with the deeply redshifted light of the young universe. It shows that darkness often means not an absence of radiation, but merely the presence of wavelengths our eyes cannot see. Beyond the violet edge of human vision lies ultraviolet radiation, a region of electromagnetic light with shorter wavelengths and more energetic photons than visible violet light. Ultraviolet radiation is less energetic than X-rays, but energetic enough to interact strongly with atoms, molecules, and living tissue. It can remove electrons, break chemical bonds, and alter the physical state of matter in ways that ordinary, visible light often cannot. This makes ultraviolet light extremely useful for astronomy, although it also makes the ultraviolet universe difficult to observe from the ground. Much of the ultraviolet radiation arriving from space is absorbed by molecular oxygen and ozone in Earth's atmosphere. The same atmospheric shield that protects life from damaging radiation prevents many ultraviolet wavelengths from reaching telescopes at the surface. Some near-ultraviolet observations can be made from high mountain sites, but much of ultraviolet astronomy requires instruments carried above the atmosphere by rockets, satellites, or space telescopes. That inconvenience has produced a remarkable scientific reward. Ultraviolet light is especially sensitive to hot stars. A star's temperature determines the wavelengths at which it emits most strongly. Cooler stars release a larger fraction of their energy in visible and infrared light. Very hot stars produce much more ultraviolet radiation. This means that ultraviolet images can reveal young stellar populations that may be less obvious in visible light. The hottest and most massive main sequence stars belong mainly to the O-type and B-type spectral classes. Their surface temperatures can range from roughly 10,000 Kelvin to well above 30,000 Kelvin. They burn through their nuclear fuel quickly and live for only a few million to a few tens of millions of years. Their presence therefore indicates that star formation has occurred relatively recently. A galaxy may appear smooth and calm in visible light, while ultraviolet observations reveal bright knots tracing young star clusters along spiral arms. These massive stars strongly influence their surroundings. Their ultraviolet photons can ionize nearby hydrogen. Ionization occurs when an atom or molecule loses one or more electrons after absorbing sufficient energy or undergoing an energetic collision. A neutral hydrogen atom contains one proton and one electron. When an ultraviolet photon removes the electron, the atom becomes an ionized proton. Large regions of gas around hot young stars can therefore become ionized. These glowing clouds are known as H2 regions, with the name indicating ionized hydrogen rather than molecular hydrogen. As free electrons later recombine with protons, the atoms emit light at characteristic wavelengths. This can make the surrounding nebula glow in visible light, even though the process is being driven by ultraviolet radiation from stars hidden within or nearby. Ultraviolet astronomy also reveals the restless outer layers of stars. The visible surface of a star is called the photosphere, but above it lie more rarefied regions such as the chromosphere and corona. The chromosphere is hotter than the photosphere in many stars and produces strong ultraviolet emission lines. The corona can reach temperatures of millions of degrees and emits ultraviolet and X-ray radiation. Ultraviolet observations can detect flares, magnetic activity, and rapidly changing structures in these outer atmospheres. They also trace stellar winds. Hot, massive stars drive powerful outflows of ionized gas. Radiation transfers momentum to atoms and ions through absorption and scattering, accelerating material away from the star. These winds can travel at thousands of kilometers per second and remove a significant fraction of a massive star's outer layers during its lifetime. Ultraviolet spectra reveal these outflows through broadened or shifted absorption lines. They can show not only that matter is moving, but roughly how quickly it is escaping. Several major observatories helped build this view of the ultraviolet sky. The International Ultraviolet Explorer was launched in 1978 and operated for more than 18 years. It allowed astronomers to obtain ultraviolet spectra of stars, galaxies, planetary nebulae, active galactic nuclei, and many other objects. The Galaxy Evolution Explorer, launched in 2003, surveyed large portions of the sky in ultraviolet light. Its observations traced star formation in nearby galaxies and revealed faint extended structures that were difficult to recognize at visible wavelengths. The Hubble Space Telescope also carries instruments capable of ultraviolet observation. Because Hubble operates above most of Earth's atmosphere, it can measure ultraviolet spectra and images that are inaccessible to ordinary ground-based telescopes. One of the most important ultraviolet signatures in astronomy comes from hydrogen. Hydrogen atoms can absorb or emit radiation when their electrons move between specific energy levels. The Lyman series involves transitions between the lowest energy level and higher levels. Most of these transitions lie in the ultraviolet. The strongest and most famous is the Lyman alpha line. Lyman alpha radiation is produced when an electron moves between the first and second energy levels of hydrogen. It is a powerful tracer of ionized and neutral gas, star-forming regions, and the material between galaxies. However, Lyman alpha photons do not travel through hydrogen gas in a simple straight path. Because hydrogen absorbs them so readily, they may be scattered many times before escaping. Dust can also absorb them during this complicated journey. Their strength and shape therefore carry information about gas motion, density, geometry, and dust content. Ultraviolet spectra of distant quasars provide an even broader view of hydrogen. A quasar is an extremely luminous active galactic nucleus, powered by matter falling towards a supermassive black hole. As ultraviolet light from a distant quasar travels towards Earth, it passes through clouds of hydrogen, distributed across intergalactic space. Each cloud absorbs Lyman alpha radiation at a particular wavelength. Because the universe is expanding, clouds at different distances have different cosmological redshifts. The result is a series of absorption lines spread across the quasar's spectrum. This pattern is called the Lyman alpha forest. Each line marks hydrogen encountered at a different point along the light's journey. The forest allows astronomers to study faint gas that would otherwise be nearly impossible to detect. It reveals how ordinary matter is distributed between galaxies and how that distribution changes across cosmic time. Ultraviolet observations also expose compact and energetic stellar systems. White dwarfs are the dense remnants left behind by stars like the Sun. Young white dwarfs can have very hot surfaces and emit strongly in ultraviolet light. In binary systems, a white dwarf, neutron star or black hole may draw matter from a companion star. The incoming gas often forms an accretion disk. Friction, turbulence, and compression heat the disk, with the hottest regions emitting ultraviolet radiation or X-rays. Ultraviolet spectra can reveal the temperature and motion of this material, along with winds flowing away from the disk. The same techniques help trace the chemical development of galaxies. Carbon, oxygen, nitrogen, and other elements produce absorption and emission lines in ultraviolet spectra, often in several different ionization states. These lines reveal how stars have gradually enriched galaxies with elements forged through nuclear fusion and stellar explosions. Different ionization states also indicate the temperature and radiation environment of the gas. Ultraviolet astronomy is therefore powerful precisely because ultraviolet photons interact so readily with matter. They ionize atoms, excite electrons, and leave clear spectral signatures. Yet this same eagerness to interact means ultraviolet light is easily absorbed by dust, gas, and Earth's atmosphere. The ultraviolet universe is generous with information, but it does not deliver that information without obstacles. Once those obstacles are overcome, a highly active cosmos appears. Young stars shine intensely. Stellar winds sweep through surrounding gas. Hot atmospheres flare and pulse. Hydrogen between galaxies records the passage of distant quasar light. Ultraviolet astronomy reveals a universe shaped by heat, ionization, rapid change, and the brief, brilliant lives of massive stars. Beyond ultraviolet light lies the X-ray region of the electromagnetic spectrum, where photons carry far more energy and wavelengths become extremely short. X-rays generally occupy the range between ultraviolet radiation and gamma rays. The boundary is not perfectly fixed. In some scientific contexts, the distinction is based less on wavelength and more on how the radiation was produced. X-rays are often associated with energetic electrons, hot gas, and atomic processes, while gamma rays are often linked with nuclear reactions or the most extreme particle interactions. Nature, as usual, is not especially concerned with keeping the labels tidy. Almost all astronomical X-rays are absorbed by Earth's atmosphere. This protects living organisms from a continuous high-energy bombardment, but it also means that X-ray astronomy cannot normally be carried out from the ground. Early observations relied on instruments carried briefly above the atmosphere by rockets. In 1962, a rocket-borne experiment led to the discovery of a powerful X-ray source in the constellation Scorpius. The object became known as Scorpius X-1. Riccardo Giacconi was among the scientists involved in the discovery. Scorpius X-1 was much brighter in X-rays than the Sun appeared at those wavelengths, revealing that the universe contained powerful high-energy sources that ordinary telescopes had completely missed. X-rays usually come from extreme physical conditions. Gas heated to millions of degrees can radiate strongly in X-rays. Charged particles moving through powerful magnetic fields can produce high-energy emission, Matter falling towards neutron stars or black holes can also become hot enough to shine across the X-ray sky. One important process is Bremsstrahlung, a German term meaning breaking radiation. Bremsstrahlung occurs when a charged particle, usually an electron, passes near an atomic nucleus. The electric field of the nucleus changes the electron's direction and speed. Because an accelerating charged particle emits radiation, this deflection produces photons. In extremely hot plasma, electrons move rapidly and repeatedly past near ions. Their combined Bremsstrahlung emission can create a broad X-ray spectrum. Hot plasma also produces distinct spectral lines. At temperatures of millions of degrees, atoms may lose many of their electrons and become highly ionized. The remaining electrons can move between allowed energy levels, producing X-ray photons at precise wavelengths. These lines reveal which elements are present and how strongly ionized they have become. Their shapes and positions can also provide information about temperature, density, and motion. If a line is shifted towards longer or shorter wavelengths, the emitting material may be moving away from or towards the observer. If it is broadened, the gas may be turbulent, rapidly rotating or spread across a range of temperatures. Several space observatories transformed X-ray astronomy. The Einstein Observatory, launched in the late 1970s, produced some of the first detailed X-ray images using focusing optics. The Röntgen satellite, launched in 1990, carried out an important survey of the X-ray sky and discovered large numbers of previously unknown sources. The Chandra X-ray Observatory, launched by the National Aeronautics and Space Administration in 1999, brought exceptionally sharp imaging to the field. The European Space Agency's X-ray multi-mirror mission, Newton combines strong collecting power with X-ray spectroscopy. The joint Japanese and American X-ray imaging and spectroscopy mission was designed to study hot plasma with highly precise measurements of X-ray energies. Many of the brightest X-ray sources involve compact objects. A neutron star is the collapsed core left behind after certain massive stars explode. A black hole is a region where gravity has become so strong that an event horizon prevents light from escaping. When gas falls towards one of these objects, it usually does not drop straight inward. Its angular momentum causes it to form a rotating accretion disk. Within the disk, friction, magnetic turbulence and collisions redistribute angular momentum. Some material gradually spirals inward, losing gravitational energy. That energy is converted into heat. Near a neutron star or black hole, the inner accretion disk can reach temperatures of millions of degrees and emit intensely in X-rays. An X-ray binary contains a compact object orbiting an ordinary companion star. The neutron star or black hole may capture gas from the companion stellar wind. In closer systems, the companion can expand until material begins to cross a gravitational boundary called the Röchloeb. This process is known as Röchloeb overflow. The transferred gas forms an accretion disk around the compact object, creating X-ray emission that can change dramatically over time. Rapid variability provides an important clue to the size of the emitting region. A source cannot normally brighten or fade coherently faster than light can travel across it. If the X-ray output changes over a fraction of a second, the source must be extremely compact. This light crossing argument helps show that the radiation is coming from a region only hundreds or thousands of kilometers across, rather than from an entire galaxy. Neutron stars can produce especially regular patterns. Many possess magnetic fields strong enough to guide in falling gas towards their magnetic poles. Matter striking these small regions becomes extremely hot and releases X-rays. If the magnetic axis is tilted relative to the rotation axis, the X-ray beams sweep across space as the neutron star turns. An observer detects a repeating pulse each time a beam crosses Earth. Some neutron stars possess even stronger magnetic fields and are known as magnetas. A magneta's magnetic field can be trillions of times stronger than Earth's field. Sudden rearrangements of that field or fractures in the neutron star's rigid outer crust can release bursts of X-rays and gamma rays. Rare giant flares can briefly become among the brightest high-energy events visible from within the Milky Way or nearby galaxies. X-rays also reveal structures far larger than individual stars. Galaxy clusters contain enormous amounts of thin gas spread between their member galaxies. This intra-cluster medium is extremely sparse by ordinary standards, but it can reach temperatures of tens of millions of degrees. At those temperatures, the gas emits X-rays through Bremsstrahlung and atomic line emission. Because galaxy clusters contain such vast volumes of plasma, their combined X-ray glow can be extremely bright. These observations allow astronomers to map the distribution and temperature of cluster gas. They can reveal shock fronts, cavities inflated by black hole jets, and the effects of collisions between entire clusters. Supernova remnants provide another important X-ray laboratory. When a star explodes, its expanding debris drives shock waves into surrounding gas. The shocked material can be heated to millions of degrees. X-ray images trace the shape of these shocks and reveal newly formed elements such as oxygen, silicon, sulfur, and iron. They also show where particles are being accelerated to very high energies, sometimes producing synchrotron X-rays near the outer edges of the remnant. The X-ray sky is therefore a map of cosmic extremity. It reveals collapsed stars only a few kilometers wide, black holes feeding from companion stars, plasma spread across millions of light years, and debris racing away from stellar explosions. Much of this universe is entirely dark in visible light. In X-rays, it becomes bright, restless, and unmistakably alive with energy. Gamma rays occupy the most energetic region of the electromagnetic spectrum. Their wavelengths are extraordinarily short, and each photon can carry far more energy than a photon of visible, ultraviolet or ordinary X-ray light. Gamma rays are commonly produced by nuclear transitions, collisions between high-energy particles, and some of the most extreme acceleration processes known in nature. The boundary between the highest energy X-rays and lower energy gamma rays is not perfectly fixed. In some cases, classification depends less on wavelength than on origin. Radiation produced by interactions involving atomic electrons may be described as X-rays, while radiation emerging from nuclear processes or very energetic particle collisions may be called gamma rays. At these energies, familiar optical technology stops being useful. Visible light can be reflected by mirrors or bent by glass lenses. Gamma rays usually pass through such materials or interact with them in ways that prevent ordinary focusing. Gamma ray telescopes must instead detect the secondary particles created when energetic photons strike matter. One important interaction is Compton scattering. During Compton scattering, a gamma-ray photon collides with an electron and transfers some of its energy to it. The photon then continues in a different direction with reduced energy. By measuring the scattered photon and the moving electron, an instrument can estimate the direction and energy of the original gamma-ray. At still higher energies, pair production becomes possible. A gamma-ray photon passing near an atomic nucleus can transform into an electron and its antimatter counterpart, a positron. The nearby nucleus helps conserve momentum during the interaction. The paths and energies of the resulting particles can then be measured. These detection methods allowed observatories to build maps of a sky that human eyes could never see. The Compton Gamma Ray Observatory, launched by the National Aeronautics and Space Administration in 1991, carried several instruments designed for different gamma-ray energies. It detected pulsars, active galactic nuclei, supernova remnants, and diffuse radiation across the Milky Way. The Fermi Gamma Ray Space Telescope later produced much more detailed surveys of the high-energy sky. It has observed thousands of gamma-ray sources, including rapidly rotating neutron stars, jets from supermassive black holes, and regions where particles are being accelerated near supernova remnants. Gamma-ray astronomy can also detect radioactive elements. Unstable atomic nuclei release characteristic gamma rays as they decay. These spectral signatures allow astronomers to trace nuclear reactions inside stellar explosions and follow the distribution of newly produced elements through space. The most dramatic gamma-ray signals are often gamma-ray bursts. These are brief flashes that can outshine nearly every other gamma-ray source in the sky for a few seconds or minutes. Gamma-ray bursts were first discovered by the United States Vela satellites during the Cold War. The satellites had been designed to detect possible nuclear explosions in space. Instead, they recorded mysterious flashes arriving from beyond Earth. The discoveries were eventually made public, and the signals were recognized as cosmic. Gamma-ray bursts are broadly divided into long-duration and short-duration events. Long-duration bursts generally last more than a few seconds and are commonly associated with the collapse of certain massive stars. These stars have exhausted their nuclear fuel and undergo catastrophic core collapse, sometimes producing unusually energetic supernovae. The collapsar model, associated with Stan Woosley and other researchers, describes a rapidly rotating massive star whose core collapses to form a black hole. Material falls inward and creates a dense accretion disk around the new black hole. Under suitable conditions, intense magnetic fields and rapid rotation launch narrow jets moving at speeds extremely close to the speed of light. If one of these jets points towards Earth, a gamma-ray burst may be detected. Short-duration bursts usually last less than a few seconds and are commonly linked with mergers involving neutron stars. A pair of neutron stars, or a neutron star and a black hole, can spiral together and collide. These mergers release gravitational waves and may also launch relativistic jets capable of producing brief gamma-ray flashes. Gamma-ray bursts are strongly beamed. Their radiation is concentrated into narrow directions rather than emitted equally in every direction. This makes a burst appear extraordinarily bright to an observer located inside the beam. The true energy is still immense, but lower than it would be if the same apparent brightness were radiated across the entire sky. After the initial flash, many bursts produce an afterglow. As the jet collides with surrounding gas, it slows and generates emission at X-ray, ultraviolet, visible, infrared, and radio wavelengths. These afterglows are essential because they last longer and can be located more precisely than the original gamma-ray flash. By studying them, astronomers can identify the host galaxy, measure the burst's distance, and investigate the environment around the explosion. Some gamma rays possess energy so high that space telescopes are no longer the most effective way to detect them. Instead, astronomers use Earth's atmosphere as part of the instrument. Facilities such as the high-energy stereoscopic system in Namibia and the major atmospheric gamma imaging Cherenkov telescopes in the Canary Islands observe faint flashes of Cherenkov light. When a very high-energy gamma ray strikes the upper atmosphere, it creates a cascade of secondary particles. These particles move through the atmosphere faster than light can travel through air, though never faster than light travels through a vacuum. Their passage produces a brief bluish flash called Cherenkov radiation. Several telescopes record the shape, brightness, and timing of the flash. From this information, astronomers reconstruct the direction and approximate energy of the original gamma ray. The universe is not equally transparent to gamma rays of every energy. During a long journey, a high-energy gamma ray can interact with a lower-energy photon from the background light filling space. Together, the two photons may create an electron and a positron. This process makes distant space increasingly opaque at certain gamma-ray energies. As a result, observations of remote gamma-ray sources reveal not only the source itself, but also the fields of background light encountered along the way. The gamma-ray sky marks the locations where nature accelerates particles to extraordinary energies. It reveals radioactive debris, rapidly spinning neutron stars, jets from supermassive black holes, and the explosive deaths of massive stars. These signals may last for years, seconds, or only a fraction of a heartbeat. However brief they appear, they come from some of the most powerful events in the observable universe. Neutrinos are among the most elusive particles in the universe. They are electrically neutral elementary particles with extremely small masses. Under the standard model of particle physics, they interact through the weak nuclear force and gravity, but not through the electromagnetic force. Because they carry no electric charge, neutrinos are not deflected by magnetic fields. They also interact with ordinary matter so rarely that they can pass through stars, planets, and human bodies, almost as though nothing were there. At every moment, enormous numbers of neutrinos produced inside the Sun are passing through Earth. Most continue onward without striking a single particle. This makes neutrinos extraordinarily difficult to detect, but it also makes them valuable messengers. Light can be absorbed, scattered, or trapped inside dense matter. Neutrinos can escape from regions that electromagnetic radiation cannot leave easily. Their existence was first proposed as a solution to a scientific puzzle. In 1930, Wolfgang Pauli suggested that an unseen neutral particle might be produced during beta decay. Beta decay is a nuclear process in which a neutron can transform into a proton while releasing an electron and another particle. Early measurements appeared to show that some energy and momentum were missing. Rather than abandon the conservation of energy, Pauli proposed that an undetected particle was carrying the missing quantities away. Enrico Fermi later developed a mathematical theory of beta decay and gave the particle its familiar name, neutrino, meaning little neutral one. For several decades, the neutrino remained a theoretical idea. In the 1950s, Clyde Cowan and Frederick Reines designed an experiment near a nuclear reactor where vast numbers of antineutrinos were being produced. They placed a detector close enough to the reactor to observe a rare interaction involving an antineutrino and a proton. The resulting particles created a distinctive sequence of signals. Although almost every antineutrino passed through the apparatus unnoticed, enough interactions occurred to confirm that the particle was real. The Sun produces neutrinos through nuclear fusion in its core. Deep inside the Sun, hydrogen nuclei are gradually converted into helium. This releases energy and produces electron neutrinos. Photons created in the solar core cannot escape directly. They are repeatedly absorbed and scattered, taking a very long time to work their way towards the surface. Neutrinos behave differently. Once produced, most leave the Sun almost immediately and travel through hundreds of thousands of kilometers of solar material with barely any interference. They provide a direct messenger from the hidden center of the Sun. Raymond Davis Jr. attempted to detect these solar neutrinos using the Homestake experiment, located deep underground in a former gold mine in South Dakota. The detector contained a large tank filled with a chlorine-based cleaning fluid. On rare occasions, an electron neutrino interacted with a chlorine atom and transformed it into radioactive argon. The number of argon atoms was extraordinarily small and had to be extracted carefully. The experiment detected solar neutrinos, but only about 1/3 of the number predicted by standard solar models. This became known as the solar neutrino problem. Either the models of the Sun were wrong, the experiments were missing something, or neutrinos were behaving in an unexpected way. Further evidence came from detectors in Japan. Masatoshi Koshiba and the Kamiokande collaboration used a large tank of ultra-pure water surrounded by sensitive photodetectors. When a neutrino interacted with a particle in the water, it could produce a fast-moving charged particle. That particle created a faint flash of Cherenkov light. Cherenkov light appears when a charged particle moves through a material faster than light can travel through that material, though never faster than light moves through a vacuum. Kamiokande was followed by the much larger Super Kamiokande detector. In Canada, the Sudbury Neutrino Observatory used heavy water, allowing it to detect electron neutrinos and also measure the total number of several neutrino types arriving from the Sun. The results showed that the missing neutrinos had not disappeared. They had changed identity. Neutrinos occur in three forms known as electron, muon, and tau flavors. The idea that neutrinos might transform between flavors was developed theoretically by Bruno Ponte-Corvo and other researchers. This process is called neutrino oscillation. A neutrino produced as an electron neutrino can later be detected as a muon neutrino or a tau neutrino. The Homestake experiment was mainly sensitive to electron neutrinos, so it appeared to find too few. The Sudbury Neutrino Observatory showed that when all accessible flavors were considered, the total agreed much more closely with predictions from solar models. Neutrino oscillation requires neutrinos to have non-zero mass. That was a major discovery because the simplest original form of the Standard Model treated neutrinos as massless particles. Their masses are extremely small, but their existence shows that the Standard Model is incomplete and must be extended. Neutrino detectors must be enormous because interactions are so rare. They often contain vast quantities of water, heavy water, ice, or another transparent material. Thousands of photodetectors search for tiny flashes of light produced when an occasional neutrino finally collides with matter. The IceCube Neutrino Observatory uses a cubic kilometre of Antarctic ice near the South Pole. Long strings of photodetectors are embedded deep beneath the surface, where the ice is clear and naturally shielded from much surface radiation. IceCube detects the faint Cherenkov light produced by charged particles created during neutrino interactions. Some of the most important neutrinos ever observed arrived from supernova 1987A. This stellar explosion occurred in the Large Magellanic Cloud, a nearby satellite galaxy of the Milky Way. Several detectors recorded a small burst of neutrinos shortly before visible light from the explosion reached Earth. The neutrinos escaped rapidly from the collapsing stellar core, while the visible light had to wait until the explosion's shock wave reached the outer layers of the star. These detections provided direct evidence about the core collapse process and confirmed that enormous quantities of energy are carried away by neutrinos. A nearby future supernova could produce a much larger neutrino signal. Detectors might provide an early warning before the explosion becomes visible, giving telescopes time to point towards the correct region of the sky. The neutrinos could reveal the behavior of matter inside the collapsing core, where temperatures and densities become extreme and ordinary light remains trapped. High-energy cosmic neutrinos may also reveal powerful accelerators beyond the Milky Way. Possible sources include blazars, where a jet from a supermassive black hole points towards Earth, and tidal disruption events, where a star is torn apart by a black hole. These associations remain an active area of research, and individual detections must be interpreted carefully. Neutrinos are difficult messengers because they almost never interact. Yet that same quality allows them to pass through the densest regions of the universe and carry information outward. They give astronomy a way to look inside stars, collapsing cores, and distant high-energy environments that light alone cannot fully reveal. Gravitational waves are ripples in the structure of space-time itself. They are not electromagnetic radiation. They do not consist of photons, and they do not travel through space-time in quite the same way as radio waves visible light or gamma rays. Instead, a gravitational wave is a moving distortion of space-time, produced when massive objects accelerate in an uneven or asymmetrical way. Albert Einstein predicted gravitational waves in 1916 as a consequence of general relativity. General relativity describes gravity not as an ordinary force pulling across empty space, but as the curvature of space-time created by mass and energy. Objects move through this curved geometry, following the straightest paths available to them. If the distribution of mass changes rapidly enough, changes in space-time curvature can spread outward as waves. Not every movement of matter produces detectable gravitational radiation. A perfectly spherical object expanding and contracting in complete symmetry would not radiate gravitational waves. From every direction, the mass distribution would still appear the same. Gravitational wave emission depends instead on changing asymmetry. In technical language, the most important contribution usually comes from a changing mass quadrupole distribution. This means that mass must move in a pattern more complicated than a simple spherical pulse. Two dense objects orbiting one another provide an ideal example. Their mass is constantly changing position in an uneven pattern, creating gravitational waves that carry energy away from the system. As those waves move through space, they alternately stretch and compress distances in perpendicular directions. Imagine a circle of freely floating particles. As a gravitational wave passes through, the circle may briefly become an ellipse stretched in one direction and squeezed in the other. A moment later, the pattern reverses. The particles are not being pushed through space by an ordinary force. The distances between them are changing because space-time itself is being distorted. Gravitational waves travel at the speed of light. However, even the strongest waves reaching Earth produce almost unimaginably small effects. A collision between black holes may release more power for a brief moment than all the stars in the observable universe combined. By the time the resulting gravitational waves cross Earth, the change in distance may be tiny beyond ordinary intuition. A detector several kilometers long may be stretched by less than 1/10,000th of the width of a proton. Measuring such a change requires extraordinary isolation, precision, and patience. The Laser Interferometer, gravitational wave observatory, was built for this purpose. It operates two major detectors in the United States, one near Hanford in Washington and another near Livingston in Louisiana. Each facility contains two long vacuum tubes arranged at right angles. The arms are roughly 4 kilometers long. A laser beam is divided into two parts. One beam travels along one arm, while the other travels along the perpendicular arm. Mirrors reflect the beams back towards the point where they began. The light is then recombined. Under normal conditions, the paths are adjusted so that the returning waves interfere in a carefully controlled pattern. If a gravitational wave passes through, one arm may become fractionally longer while the other becomes fractionally shorter. The travel times of the laser beams change by a minuscule amount, altering the interference pattern. This technique is called laser interferometry. The principle is simple enough to describe, but the practical instrument must contend with seismic vibrations, thermal motion, passing vehicles, ocean waves, atmospheric disturbances, and countless other sources of noise. The universe may whisper while the local environment has a habit of moving furniture. Rainer Weiss developed important early designs for laser interferometers and studied the sources of noise that such detectors would face. Kip Thorne advanced the theoretical understanding of gravitational wave sources and what their signals might reveal. Barry Barish played a central role in transforming the project into a large and effective international scientific collaboration. Their contributions formed part of a much wider effort involving the Laser Interferometer Gravitational Wave Observatory Scientific Collaboration. Engineers, universities and research institutions across many countries. The first direct detection was observed in September 2015 and announced in February 2016. The signal came from two stellar mass black holes spiraling together more than 1 billion light-years away. The event unfolded in several recognizable stages. During the inspiral, the black holes orbited one another repeatedly. As gravitational waves carried energy away, the orbit shrank and the objects moved faster. The signal increased in frequency and strength, producing a pattern often described as a chirp. The black holes then entered the merger phase, when their horizons combined and the space-time around them changed violently. A final stage called ring down followed. The newly formed black hole was initially distorted. It settled into a stable, rotating shape by releasing gravitational waves at characteristic frequencies, rather like a struck bell gradually losing its vibrations. The complete waveform contained detailed information. Its changing frequency and amplitude revealed the masses of the original black holes. More subtle features provided clues about their spins, the orientation of the system, and its distance from Earth. Before gravitational wave astronomy, isolated pairs of black holes could be extremely difficult to find. If they were not feeding on surrounding gas, they might produce little or no visible light, X-rays or radio emission. Gravitational waves allowed astronomers to detect black holes through their motion alone. They did not need to shine. Additional detectors improved this new form of astronomy. The Virgo interferometer operates near Pisa in Italy. The Kamioka gravitational wave detector is located underground in Japan. When several observatories detect the same event, differences in arrival time help identify the region of sky from which the waves came. A global network therefore improves localization and allows electromagnetic telescopes to search for possible light from the same event. Ground-based interferometers are sensitive mainly to waves produced by compact objects such as stellar mass black holes and neutron stars. Other frequencies require different methods. Pulsar timing arrays use rapidly rotating neutron stars as a galaxy-sized detection system. Millisecond pulsars send radio pulses towards Earth with remarkable regularity. If a very low-frequency gravitational wave passes between Earth and a group of pulsars, it can create tiny correlated changes in the arrival times of their pulses. Collaborations, including the North American Nanohertz Observatory for Gravitational Waves and the International Pulsar Timing Array, search for these patterns. They are especially sensitive to waves produced by populations of orbiting supermassive black holes. Still lower frequencies will be explored in space. The planned laser interferometer space antenna will use 3 spacecraft separated by millions of kilometers. Laser beams traveling between the spacecraft will monitor changes in their relative distances. This enormous detector will search for gravitational waves from massive black hole mergers, compact binary systems, and other sources too low in frequency for ground-based observatories. Gravitational waves have added a fundamentally different sense to astronomy. Light reveals how matter emits, absorbs, and scatters radiation. Gravitational waves reveal how mass moves through gravity itself. They allow the universe to be studied not only through what shines, but through the faint and soundless trembling of space-time. Dark matter is the name given to an unseen form of matter whose presence is inferred mainly through gravity. It has not been photographed as a separate substance, collected in a container, or conclusively identified as one particular particle. The term describes a physical mystery rather than a completed discovery. Something appears to supply additional gravity throughout galaxies, galaxy clusters, and the wider universe. Whatever that something is, it does not seem to emit, absorb, or reflect measurable electromagnetic radiation in the ordinary way. A cloud of gas may be dark in visible light but bright in radio or infrared wavelengths. Dark matter is different. Conventional telescopes have not found a wavelength at which it simply begins to glow. Its presence is revealed instead by watching how visible objects move and how light travels through gravitational fields. One of the earliest major clues came from Fritz Zwicky. In 1933, Zwicky studied galaxies inside the Coma cluster. By measuring their motions, he estimated how much mass would be required to keep the cluster gravitationally bound. The visible galaxies did not appear to contain nearly enough matter. If only the luminous material were present, many of the galaxies seemed to be moving so quickly that the cluster should have dispersed. Zwicky proposed that a large amount of unseen matter was contributing additional gravity. He referred to it using a German phrase meaning dark matter. The idea attracted more attention several decades later through studies of galaxy rotation. Vera Rubin and Kent Ford measured the speeds of stars and glowing gas at different distances from the centres of spiral galaxies. Their observations built on work by several other astronomers, but they helped establish the problem with exceptional clarity. In a simple model where most of a galaxy's mass is concentrated in its visible central regions, orbital speed should eventually decrease with distance. The solar system provides a familiar example. Neptune moves around the Sun more slowly than Earth because it lies farther from the mass that dominates the system. A similar decline was expected in galaxies once observations reached beyond most of the bright stars. Instead, many galactic rotation curves remained comparatively flat. Stars and gas far from the centre continued orbiting at unexpectedly high speeds. The visible matter alone could not provide enough gravity to explain those motions. The most common interpretation is that galaxies are surrounded by dark matter halos. These halos are thought to be much larger than the visible disks of spiral galaxies. They are often described as approximately spherical, although their precise shapes can vary and remain difficult to measure. The luminous galaxy sits inside this much broader distribution of unseen mass. Dark matter can also be inferred through gravitational lensing. According to Albert Einstein's general theory of relativity, mass curves space-time. Light travelling through that curved geometry follows a deflected path. A massive foreground object can therefore bend light from something more distant. Strong gravitational lensing occurs when the alignment and mass are sufficient to create clearly distorted arcs, multiple images, or sometimes an almost complete ring around the foreground object. By measuring those distortions, astronomers can estimate the total mass responsible, whether that mass shines or not. Weak gravitational lensing produces much subtler changes. Individual background galaxies may be stretched only slightly, but the average distortion across large numbers of galaxies reveals the distribution of mass over broad regions of the sky. Gravitational microlensing occurs when a compact foreground object passes close to the line of sight towards a more distant star. The foreground object temporarily magnifies the background light. Unlike strong lensing, microlensing may not produce separately resolved images. It appears instead as a characteristic brightening and fading. These methods allow gravity to act as a kind of indirect camera. One particularly important example is the Bullet cluster, a system created by the collision of two galaxy clusters. Most ordinary matter in a galaxy cluster exists not in the galaxies themselves, but in hot gas between them. During the collision, that gas interacted, slowed and became concentrated in a central region. X-ray observations reveal where much of this hot ordinary matter is located. The galaxies pass through one another more freely. Gravitational lensing showed that much of the system's total mass was centered closer to the galaxies than to the slowed X-ray gas. This separation suggests the presence of a large mass component that interacts weakly with ordinary matter and with itself, apart from gravity. The bullet cluster is therefore strong evidence for something behaving like dark matter. It does not, however, reveal what dark matter is made from. Cosmological observations provide another line of evidence. Measurements of the cosmic microwave background, the growth of galaxies, and the large-scale distribution of matter indicate that ordinary baryonic matter forms only a minority of the universe's total matter. Baryonic matter includes atoms and the particles that make up familiar objects, stars, planets, gas, dust, and people, listening patiently to descriptions of invisible substances. Within the standard lambda cold dark matter cosmological model, most matter is non-baryonic dark matter. It appears to have played a central role in cosmic structure formation. Dark matter began gathering under gravity in the early universe. Ordinary gas then fell into these gravitational wells, eventually forming stars and galaxies. Without dark matter, the structures observed today would have been much harder to assemble within the available cosmic time. Many possible dark matter particles have been proposed. Weakly interacting massive particles were long considered leading candidates. They would possess mass and interact only weakly with ordinary particles, making them difficult but perhaps not impossible to detect. Axions are hypothetical particles originally proposed in connection with a problem in the theory of the strong nuclear force. Certain axion models could also provide the required dark matter. Sterile neutrinos are another possibility. Unlike the three known neutrino flavors, they would not participate in ordinary weak force interactions, although they might mix slightly with familiar neutrinos. None of these candidates has been confirmed as the dominant dark matter particle. Scientists searched through several experimental approaches. Underground direct detection experiments use carefully shielded detectors to search for rare collisions between dark matter particles and atomic nuclei. They are placed deep beneath rock to reduce interference from cosmic rays and other background radiation. Collider experiments at the European Organization for Nuclear Research attempt to create new particles in high-energy collisions. A dark matter particle would not be detected directly inside the apparatus. Its presence might instead be inferred from missing energy and momentum, provided the signal could be distinguished from known processes. Indirect searches look for photons, neutrinos, or other particles that might be produced if dark matter particles annihilate or decay. So far, no result has provided universally accepted proof. There are also alternatives to particle dark matter. Mordechai-Milgrom introduced modified Newtonian dynamics, which proposes that the behavior of gravity or motion changes at extremely low accelerations. This approach can reproduce some galactic rotation patterns with notable success. However, modified gravity theories face the broader challenge of explaining galaxy clusters, gravitational lensing, the cosmic microwave background, and the growth of large-scale structure at the same time. Dark matter models also face unresolved questions, particularly on the smaller scales of individual galaxies. The scientific debate is therefore not simply between an established substance and an obviously incorrect alternative. It is a continuing attempt to find one framework that explains all the evidence consistently. Dark matter is invisible not because astronomers have failed to build a sufficiently powerful ordinary telescope. Its known behavior appears to be dominated by gravity rather than light. We cannot yet say what it is. We can say where its gravity acts, how strongly it influences motion, and how deeply it has shaped the visible universe. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. The name sounds reassuringly definite, but the underlying physics remains uncertain. Dark energy is not a substance that has been collected, photographed, or identified in a laboratory. It is the label attached to an observed behavior of the universe that current cosmology must explain. Cosmic expansion is sometimes imagined as an explosion, throwing galaxies outward into pre-existing empty space. That picture is misleading. The universe is not expanding from one central point into a larger surrounding emptiness. Instead, on sufficiently large scales, the distances between unbound regions increase because the scale of space itself changes over time. Galaxies held together by gravity do not expand internally in the same way. Neither do stars, planets, or people. Local forces easily overcome the tiny effect of cosmic expansion across such small distances. Across millions and billions of light years, however, the changing scale of space becomes measurable. The modern understanding of expansion developed through both theory and observation. Georges Lemaire used Albert Einstein's general theory of relativity to describe a universe that could evolve rather than remain permanently static. He connected this changing geometry with the observed recession of distant galaxies. Edwin Hubble later published measurements showing that more distant galaxies generally appeared to recede more quickly. The recession was inferred through cosmological redshift, in which light travelling through expanding space is stretched towards longer wavelengths. For much of the 20th century, astronomers expected gravity to slow the expansion. The major question seemed to be whether the expansion would continue forever, or eventually reverse. The answer changed in the late 1990s through observations of distant stellar explosions. Type 1. Supernovae occur in systems involving white dwarfs. Their peak brightness is not perfectly identical, but relationships between the shape of their light curves and their intrinsic luminosity allow them to be standardized. A light curve records how an object brightens and fades over time. Once the intrinsic luminosity of a Type 1a supernova has been estimated, astronomers can compare it with the apparent brightness seen from Earth. This provides a measure of distance. The Supernova Cosmology Project, led by Saul Perlmutter and the High-Z Supernova Search Team, associated with Brian Schmidt and Adam Rees, studied supernovae at great cosmological distances. Their results indicated that the distant explosions were dimmer than expected in a universe whose expansion had been steadily slowing. The simplest interpretation was surprising. The expansion had been slower in the past than it is today. In other words, cosmic expansion was accelerating. This discovery did not reveal the cause directly. It revealed an effect that required an explanation. The mathematically simplest possibility is Albert Einstein's cosmological constant. Einstein originally introduced this term into the equations of general relativity while attempting to describe a static universe. Once cosmic expansion became accepted, the term was often regarded as unnecessary. It later returned in a very different role. A cosmological constant behaves like an energy density built into empty space. As space expands, the density remains approximately constant. This leads to a peculiar consequence. The amount of ordinary matter in a fixed expanding region becomes more diluted as the volume grows. A cosmological constant does not dilute in the same way. Its influence, therefore, becomes increasingly important as the universe expands. Within the standard lambda-cold dark matter cosmological model, dark energy accounts for roughly 2/3 of the total cosmic energy density. The exact value depends on the data sets, assumptions, and cosmological model being used, but the broad conclusion is that dark energy dominates the present large-scale energy budget. Cosmologists often describe dark energy using an equation of state parameter. This relates pressure to energy density. Ordinary matter has familiar forms of pressure. Gas pressure, for example, comes from particles colliding and transferring momentum. Dark energy behaves differently. A cosmological constant has negative pressure in the equations of general relativity. This does not mean that empty space feels like a household vacuum pulling inward. Negative pressure contributes to gravity in a way that can drive accelerated expansion. General relativity allows pressure, as well as mass and energy density, to influence the curvature of space-time. Under the appropriate conditions, sufficiently negative pressure produces large-scale gravitational repulsion. The cosmological constant is not the only possibility. Quintessence describes a hypothetical dynamic form of dark energy associated with a field that changes over time and space. Other models involve evolving scalar fields with different physical properties. Some researchers investigate whether the acceleration indicates that general relativity must be modified across enormous cosmological distances. In those models, the problem may not be an unknown component filling space, but an incomplete description of gravity on the larger scales. Any successful explanation must match several independent observations. Type 1. A supernovae measure the expansion history through distance and brightness. Baryon acoustic oscillations provide a characteristic scale in the distribution of galaxies inherited from pressure waves in the early universe. Measurements of the cosmic microwave background constrain the geometry and contents of the young cosmos. Weak gravitational lensing traces the distribution and growth of mass by measuring subtle distortions in the shapes of distant galaxies. Galaxy clustering reveals how cosmic structure has developed over time. These methods test different aspects of cosmology. Their combined agreement is far more powerful than relying on one kind of observation alone. Large surveys have been designed to improve these measurements. The Dark Energy Survey mapped hundreds of millions of galaxies and studied supernovae, galaxy clusters, weak lensing and large-scale structure. The European Space Agency's Euclid mission is designed to investigate the geometry of the universe and the growth of cosmic structure across billions of years. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will repeatedly image large areas of the southern sky, identifying enormous numbers of galaxies, supernovae, and changing objects. Together, these surveys aim to determine whether dark energy behaves exactly like a cosmological constant or shows signs of evolution. Dark energy should not be confused with dark matter. Dark matter attracts gravitationally. It gathers into halos, helps galaxies form and strengthens the growth of cosmic structure. Dark energy does not clump around galaxies in the same way. Its known role is associated with the accelerated expansion of space across the larger scales. One helps draw matter together. The other appears to increase the separation between sufficiently distant, unbound regions. Dark energy is invisible in an unusually deep sense. It is not known through light, particles, or a direct local detection. It is known mainly through the changing behavior of space across billions of light years. One of the dominant components of the universe has revealed itself not by shining, but by altering the history of cosmic expansion. Magnetic fields form an invisible framework throughout the universe. They influence charged particles, guide streams of plasma, and shape the behavior of stars, planets, nebulae, galaxies, and even galaxy clusters. They rarely announce themselves through ordinary brightness, yet their effects can be traced across enormous distances. A magnetic field can alter the path of an electrically charged particle. Electrons and atomic nuclei moving through space may spiral around magnetic field lines, become trapped within magnetic structures, or be accelerated when those fields change. Because much of the visible universe consists of plasma, meaning gas in which electrons have been separated from atomic nuclei, magnetism plays a central role in astrophysics. The field itself cannot usually be photographed in the same direct way as a glowing star or cloud. Instead, astronomers infer its presence by observing what it does to matter and radiation. One important method involves Zeeman splitting. This effect was discovered by the Dutch physicist Peter Zeeman in the late 19th century. Atoms and molecules emit or absorb light at specific wavelengths determined by their internal energy levels. When those particles sit inside a magnetic field, the energy levels can shift slightly. A single spectral line may then divide into several closely spaced components. The size of this splitting reveals the strength of the magnetic field, while the pattern can provide information about its direction. Zeeman splitting is used to study magnetic fields in sunspots, stars, gas clouds, and other astronomical environments. The effect can be subtle, but it offers a direct physical measurement rather than a purely visual impression. Another major source of information is polarization. Electromagnetic radiation consists of changing electric and magnetic fields. Polarization describes the preferred orientation of those oscillations. Ordinary light may contain waves oriented in many directions. Under certain physical conditions, however, one orientation becomes more common than others. Dust grains can align with magnetic fields and preferentially absorb or emit particular orientations of light. By measuring the polarization of radiation passing through or emerging from a dusty region, astronomers can infer the direction of the surrounding magnetic field. Radio waves provide another useful effect known as Faraday rotation, named after Michael Faraday. When linearly polarized radio waves pass through a magnetized plasma, the orientation of their polarization rotates. The amount of rotation depends on the strength of the magnetic field, the number of free electrons, and the wavelength of the radiation. By observing this effect at several radio wavelengths, astronomers can estimate the magnetic field along the line of sight and study the ionized material through which the waves have travelled. Synchrotron radiation offers an even broader view. This radiation is produced when high-energy charged particles, usually electrons, spiral through magnetic fields. Synchrotron emission is naturally polarized. Its orientation and intensity can therefore reveal how ordered or tangled a magnetic field is. Radio observations use this property to map magnetic structures in supernova remnants, relativistic jets, and entire galaxies. A supernova remnant may contain field lines compressed and twisted by an expanding shock wave. A jet from a supermassive black hole may remain narrow across thousands of light years, partly because magnetic fields guide the moving plasma. Our own sun is governed by magnetic activity. The sun's magnetic field is generated by moving electrically conducting plasma within its interior. Because different parts of the sun rotate at different rates, magnetic field lines become stretched, twisted, and reorganized. This activity follows an approximately 11-year cycle. During periods of strong magnetic activity, the number of sunspots increases. Sunspots appear darker because concentrated magnetic fields suppress some of the hot rising plasma beneath them, making those regions cooler than their surroundings. Magnetic energy can also be released suddenly. Solar flares produce intense bursts of radiation, while coronal mass ejections launch enormous clouds of magnetized plasma into space. These events can disturb satellites, radio communication, and electrical systems when they reach Earth. Earth possesses its own magnetic field, generated mainly by the motion of electrically conducting liquid iron in the outer core. This field forms the magnetosphere, a vast region around the planet that interacts with the solar wind. The solar wind is a stream of charged particles flowing outward from the sun. Most of these particles are diverted around Earth by the magnetosphere. Some are guided towards the polar regions, where they collide with atoms and molecules in the upper atmosphere. Those collisions produce the aurora borealis and aurora australis. The resulting curtains of green, red, and violet light are visible evidence of an otherwise invisible magnetic structure extending far beyond the atmosphere. The Milky Way also contains a large-scale magnetic field. It runs through the galactic disk and interacts with gas, dust, and cosmic rays. Superimposed upon it are smaller turbulent fields produced by stellar winds, supernova explosions, and the chaotic motion of interstellar plasma. Faraday rotation, polarized dust emission, and synchrotron radiation all help map this complicated magnetic environment. Magnetic fields also influence the birth of stars. Stars form when dense regions within molecular clouds collapse under gravity. A magnetic field can resist some of that collapse by adding pressure and tension to the gas. It may also guide matter along preferred directions, redistribute angular momentum, or help launch outflows from young stellar objects. The result depends on the field's strength, shape, and relationship with turbulence. Magnetism does not simply prevent star formation or cause it. It participates in a complicated balance between gravity, gas pressure, turbulence, and rotation. The study of conducting fluids interacting with magnetic fields is called magnetohydrodynamics. It combines the behavior of fluids with the laws of electromagnetism and is essential for understanding stars, accretion disks, jets, and interstellar gas. One of its most energetic processes is magnetic reconnection. Magnetic field lines can become twisted and pressed together in unstable arrangements. During reconnection, their structure changes rapidly. Stored magnetic energy is converted into heat, motion, and particle acceleration. This process helps power solar flares, disturbances in Earth's magnetosphere, and energetic activity in many astrophysical plasmas. The ultimate origin of cosmic magnetic fields remains uncertain. Weak primordial seed fields may have formed in the early universe. Later, the motion of conducting plasma could have amplified them through dynamo processes inside stars and galaxies. A dynamo converts the kinetic energy of moving fluid into magnetic energy, allowing initially weak fields to grow stronger and become more organized. Exactly how the first fields formed and how quickly they spread through young galaxies and the wider cosmos is still under investigation. Magnetic fields are therefore an invisible organizing influence. They shape glowing matter without needing to glow themselves. By tracing split spectral lines, rotated polarization, and spiraling particles, astronomy reveals a hidden structure woven through the luminous universe. A black hole is invisible in a very precise sense. Under classical general relativity, no ordinary light can escape from inside its event horizon. An isolated black hole surrounded by complete darkness would therefore emit no visible signal from within that boundary. Yet black holes are not beyond observation. Astronomers find them by studying what happens around them. Gravity alters the motion of nearby stars. Falling gas becomes hot and produces radiation. Merge in black holes create gravitational waves. Their concentrated mass bends the light of more distant objects. A black hole may not shine, but the universe responds to its presence in ways that can be measured. The event horizon is the defining boundary. It is not a solid surface. It is a causal boundary in space-time. Once matter or light crosses it, no path leads back to the external universe, at least according to the classical description provided by general relativity. To a distant observer, the event horizon marks the region beyond which information can no longer return. This does not mean that a black hole pulls in everything around it like an enormous vacuum cleaner. At a reasonable distance, its gravity behaves like the gravity of any other object with the same mass. If the Sun were somehow replaced by a black hole of exactly one solar mass, Earth would continue orbiting in almost the same way. The planet would become extremely cold, which would be a fairly significant inconvenience, but it would not immediately spiral inward. Objects fall into black holes when their paths carry them too close, or when they lose enough orbital energy and angular momentum. Many stellar mass black holes are discovered in binary systems. A visible star may orbit an unseen companion. By measuring the star's speed and orbital period, astronomers can estimate the mass of the hidden object. If the unseen companion is too massive to be a neutron star and emits little or no ordinary starlight, it becomes a strong black hole candidate. The system may also produce X-rays if gas flows from the visible star towards the compact object. Gas rarely falls straight inward. It usually carries angular momentum, meaning it has rotational motion around the black hole. This causes the material to form an accretion disk. The gas in the disk orbits at different speeds depending on its distance from the center. Inner material moves faster than outer material. Magnetic fields and turbulence create stresses between neighboring regions, allowing angular momentum to move outward. As angular momentum is transferred away, some gas can spiral inward. The falling material loses gravitational potential energy. Much of that energy is converted into heat, motion, and radiation. Near a stellar mass black hole, the inner accretion disk can reach temperatures of millions of degrees and shine strongly in X-rays. This light does not come from inside the event horizon. It comes from matter still outside, heated while approaching the black hole. General relativity predicts that stable circular orbits cannot continue all the way to the horizon. There is an innermost stable circular orbit. Inside this boundary, matter cannot remain on a stable circular path and begins plunging rapidly inward. The location of the innermost stable circular orbit depends on the black hole's spin. A rotating black hole is described by the Kerr solution of general relativity, developed by Roy Kerr. If the disk rotates in the same direction as the black hole, stable orbits can extend close to the event horizon. If the disk rotates in the opposite direction, the innermost stable orbit lies farther away. This affects the temperature and efficiency of the accretion disk. By studying X-ray spectra and variability, astronomers can estimate how rapidly some black holes are spinning. Accreting black holes can also produce enormous relativistic jets. These narrow streams of plasma may move at speeds close to the speed of light and extend far beyond the surrounding system. The jets do not emerge from inside the event horizon. They are launched from the magnetized region outside it, involving the accretion disk, rotating plasma, and powerful magnetic fields. In some models, magnetic fields extract rotational energy from the black hole itself through the surrounding space-time. In others, they redirect energy from the accretion disk. The exact details remain an active area of research, but the important point is clear. Nothing escapes from within the horizon. The jet is created outside it. At the center of the Milky Way lies the compact radio source known as Sagittarius A star. It is hidden from visible light telescopes by dense interstellar dust. Infrared and radio wavelengths provide a much clearer view of the region. For decades, research teams led by Reinhard Genzel and Andrea Ghez tracked stars moving around the galactic center. These stars follow extremely tight and rapid orbits around an apparently empty point. One star, often called S2, completes an orbit in roughly 16 years. Near its closest approach, it moves at several thousand kilometers per second. The observed orbits require a mass of roughly 4 million suns, concentrated inside a remarkably small region. No known cluster of ordinary stars or stellar remnants could remain stable at that density for long. The evidence points overwhelmingly towards a supermassive black hole. Infrared measurements of these stellar orbits also allow tests of general relativity in a strong gravitational field. As stars pass close to Sagittarius A star, astronomers can measure relativistic effects in their motion and in the wavelengths of their light. An even closer view has been provided by the Event Horizon Telescope collaboration. The Event Horizon Telescope is not one single instrument. It is a global network of radio observatories using very long baseline interferometry at millimeter wavelengths. Telescopes separated by thousands of kilometers observe the same source with carefully synchronized timing. Their data are combined to create an effective aperture comparable in size to Earth. This provides the angular resolution needed to study structures on scales similar to the event horizons of nearby supermassive black holes. The collaboration released an image of the black hole in the galaxy, Messier 87, in 2019. The image showed a bright, uneven ring surrounding a dark central region. In 2022, the collaboration released a corresponding image of Sagittarius A star. These images are often described as photographs of black holes, but that phrase needs careful interpretation. The Event Horizon Telescope did not photograph the event horizon as though it were a solid dark surface. It reconstructed millimeter wave emission from hot plasma moving through strongly curved space-time around the black hole. Gravity bends the paths of photons, causing light from different parts of the plasma to wrap around the central region. The dark area is associated with the black hole shadow. The shadow is larger than the event horizon itself, because light near the black hole can be captured or deflected away from the observer. The surrounding ring is produced by radiation from hot plasma, strongly distorted and magnified by gravity. Messier 87 star and Sagittarius. A star differ greatly. The black hole in Messier 87 has a mass of several billion suns, while Sagittarius A star has only a few million solar masses. Because the smaller system changes much more quickly, reconstructing its image was especially difficult. The plasma around Sagittarius A star could vary during the observations, rather like trying to photograph a restless subject while building the camera at the same time. Black holes can also be detected without light. Gravitational wave observatories measure the ripples in space-time produced when two black holes spiral together and merge. The changing waveform reveals their masses and spins. In many cases, no electromagnetic counterpart is detected at all. The black holes may merge in an environment with too little surrounding matter to produce visible light, radio waves, or X-rays. Even then, their motion leaves a measurable gravitational signal. Isolated black holes may also reveal themselves through gravitational lensing. A black hole passing in front of a more distant star can bend and magnify the star's light. This temporary brightening is known as gravitational microlensing. The foreground object may also cause a tiny apparent shift in the background star's position. This is called an astrometric shift. By measuring both the brightening and the positional change, astronomers can estimate the lensing object's mass and distinguish a possible black hole from a lower mass star. Black holes are therefore ideal examples of invisible astronomy. Their event horizons emit no ordinary light from within, yet their gravity reorganizes the space around them. They accelerate gas, disturb stars, launch environments capable of producing jets, bend passing light and shake space-time during collisions. A black hole is seen through effects rather than through a luminous surface. It remains dark while everything nearby quietly reveals where it is. For most of its history, astronomy divided the universe according to the kind of signal being observed. Radio telescopes studied radio waves. Optical telescopes collected visible light. X-ray observatories examined hot gas and compact objects. Gamma-ray detectors searched for the most energetic photons. Each method revealed something important, but each also left parts of the story hidden. Multi-messenger astronomy brings these different forms of information together. It combines electromagnetic radiation, gravitational waves, neutrinos, and cosmic particles associated with the same source or with the same wider population of sources. Each messenger is produced by different physical processes and interacts with matter in a different way. Electromagnetic radiation can reveal temperature, chemical composition, magnetic fields, and the motion of glowing material. Yet light may be absorbed by dust, scattered by gas, or trapped inside dense matter. Neutrinos pass through matter far more easily, carrying information from stellar cores and energetic particle collisions. Their weakness is that they are extremely difficult to detect and often provide only a rough direction of origin. Cosmic rays offer direct samples of high-energy particles, but magnetic fields bend the paths of charged particles, making their sources difficult to trace. Gravitational waves travel through matter almost undisturbed and reveal the motion of massive compact objects. However, they do not usually describe the surrounding gas, chemical elements, or radiation environment. One messenger can therefore compensate for the limitations of another. The value of this approach became spectacularly clear on the 17th of August 2017. On that day, the Laser Interferometer Gravitational Wave Observatory and the Virgo detector observed a signal from two neutron stars spiraling together and merging. The event became known as Gravitational Wave Event 170817. Its waveform lasted much longer than the brief signals produced by many merging black hole pairs. As the neutron stars orbited faster and moved closer together, the gravitational wave frequency rose through the sensitive range of the detectors. From the waveform, scientists estimated the masses of the objects and recognized that they were consistent with neutron stars rather than ordinary stellar mass black holes. The signal did not arrive alone. Roughly 2 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst. The International Gamma Ray Astrophysics Laboratory also recorded the burst. For decades, astronomers had suspected that at least some short gamma-ray bursts were produced by mergers involving neutron stars. Now, gravitational waves and gamma rays had been observed from what appeared to be the same event. The gravitational wave detectors did not identify one exact point on the sky. Instead, they provided a broad localization region covering many square degrees. Observatories around the world began searching. Robotic telescopes and large survey instruments examined galaxies within the likely region. Astronomers compared new images with earlier observations, looking for a point of light that had not been present before. A new optical source was found in the galaxy known as New General Catalogue 4993, located roughly 130 million light-years away. The transient source brightened and changed rapidly. It was not an ordinary supernova. The event was a kilonova, produced by radioactive material ejected during the neutron-star merger. As the two neutron stars collided, some matter was thrown outward at a substantial fraction of the speed of light. This material was extremely rich in neutrons. Inside the expanding debris, atomic nuclei captured neutrons rapidly. This process is known as rapid neutron capture nucleosynthesis. A nucleus may capture several neutrons before it has time to undergo radioactive decay. It then transforms through a sequence of nuclear reactions, producing elements much heavier than iron. Neutron star mergers are now recognized as important sites for the formation of heavy elements such as gold, platinum, and the lanthanides. Lanthanides are a group of heavy elements with complex atomic structures. They absorb light strongly and can make kilonova material appear redder at later times. Observations across ultraviolet, visible, and infrared wavelengths followed the changing emission. The early light contained a relatively blue component, suggesting faster-moving material with fewer heavy lanthanide elements. Over the following days, the emission shifted towards red and infrared wavelengths, As the debris expanded, cooled, and became increasingly influenced by heavier radioactive nuclei. This change in colour and brightness provided information about the amount, speed, and composition of the ejected material. The event offered striking evidence that neutron star mergers contribute to the cosmic production of heavy elements. They may not be the only source of every element created through rapid neutron capture. Certain rare stellar explosions or other environments may also contribute, and the importance of each source may have changed over cosmic history. Still, the merger demonstrated directly that substantial quantities of heavy nuclei can be produced when neutron stars collide. The timing of the signals also provided a test of fundamental physics. The gravitational waves and gamma rays travelled for roughly 130 million years before reaching Earth, yet they arrived only about 2 seconds apart. Some of that delay may have arisen from the time required for the merger to launch a gamma-ray producing jet. Even so, the tiny arrival difference showed that the propagation speeds of gravity and light are extraordinarily similar. Many theories that predicted a significant difference were strongly constrained or ruled out. The combined observations also supported the connection between short gamma-ray bursts and neutron star mergers. The gamma-ray burst itself appeared comparatively faint, possibly because the narrow relativistic jet was not pointed directly towards Earth. Later, X-ray and radio observations brightened as the jet interacted with the surrounding material, and its expanding emission became easier to observe from our viewing angle. This continued monitoring showed why multi-messenger astronomy is more than the simple collection of several signals. The gravitational waves revealed the movement and masses of the merging neutron stars. The gamma rays indicated the creation of an energetic jet. Ultraviolet, visible and infrared light traced radioactive debris and heavy element formation. X-rays and radio waves revealed the later interaction between the outflow and its environment. Together they created a physical account that none of the individual observations could have provided alone. Neutrino astronomy uses a similar coordinated approach. When an observatory detects a high-energy neutrino, automated alert systems can distribute an estimated arrival direction to telescopes around the world. Those instruments then search the relevant region for active galaxies, stellar explosions, or other unusual sources. One important example involved a neutrino detected by the IceCube Neutrino Observatory, and a blazar designated TXS 0506 plus 056. A blazar is an active galactic nucleus with a relativistic jet aimed roughly towards Earth. The source was showing enhanced gamma-ray activity near the time of the neutrino detection. Follow-up studies also identified earlier neutrino activity from the same general direction. The association suggested that blazar jets may accelerate particles strongly enough to produce high-energy neutrinos. However, individual event associations require statistical caution. The sky contains many variable sources, and a neutrino direction may cover a significant area. Researchers must estimate how likely it is that a possible counterpart appeared by coincidence. Multi-messenger astronomy depends as much on coordination as on hardware. Robotic telescopes must respond quickly. Observatories must distribute alerts in usable formats. Data from different instruments must be calibrated, compared and interpreted across international teams. A cosmic event may last only seconds, while the scientific investigation involves detectors on several continents and in orbit around Earth. The universe provides the signal once. Astronomers must be organized enough not to miss the appointment. This approach is changing the way astronomy is understood. The field is no longer divided only by wavelength. Instead of asking what the radio sky, optical sky, or X-ray sky looks like in isolation, scientists increasingly ask which messengers were produced by the same physical event. Light, particles, and ripples in space-time become different witnesses. Each provides an incomplete account. Together they turn a distant flash or collision into something closer to a full cosmic investigation. Many of the most celebrated images in astronomy are not photographs in the ordinary everyday sense. They are scientific visualizations built from measurements. A camera held beneath the night sky records visible light in roughly the same region of the electromagnetic spectrum that human eyes can detect. Radio waves, infrared radiation, ultraviolet light, X-rays and gamma rays cannot be seen directly by the eye, yet instruments can measure them. The resulting data can then be translated into forms that human vision is able to interpret. A detector may record where a photon arrived, when it arrived, and how much energy it carried. Other instruments measure wavelength, polarization, or the strength of an electrical signal produced when radiation interacts with a specialized material. A single observation may contain millions or billions of numerical values. These measurements are the raw ingredients from which an astronomical image is created. In visible light astronomy, the process may resemble ordinary photography more closely. Even then, the detector usually records separate exposures through different filters rather than producing a complete color image immediately. For invisible wavelengths, the translation is more deliberate. Scientists often use representative color or false color. Representative color assigns visible colors to measurements that human eyes could not naturally perceive. Radio emission might be displayed in red, X-rays in blue, and infrared radiation in orange. The selected colors can be chosen to separate wavelengths, temperatures, chemical elements, or physical mechanisms. False color does not mean false information. The underlying radiation was genuinely detected. The positions, intensities, and measured energies are real. Only the final mapping into visible color has been chosen. A weather map provides a familiar comparison. Air temperature is not naturally blue in one place and red in another, yet the color scale makes the pattern easier to understand. Astronomical color maps serve a similar purpose, although sometimes with considerably more dramatic clouds. Radio astronomy requires especially careful image reconstruction. A single radio dish can scan the sky and record signal strength from different directions. An interferometer works differently. Several separated antennas observe the same source. Rather than taking one conventional snapshot, the array measures relationships between the arriving radio waves at different locations. These measurements sample what is known as spatial frequency information. Broad structures and fine details correspond to different spatial frequencies. The separation and orientation of each pair of antennas determine which part of that information is measured. The data must then be combined mathematically to reconstruct an image of the sky. This process is called aperture synthesis. A group of radio antennas can imitate some of the resolving power of a much larger telescope, whose diameter is comparable to the greatest distance between the antennas. Earth's rotation helps improve the result. As the planet turns, the apparent orientation of each antenna pair changes relative to the source. Over several hours, the array samples additional spatial frequencies. The physical antennas remain on the ground, but their changing geometry gradually fills part of a virtual aperture. Even with this assistance, the coverage is incomplete. The reconstructed image may contain artificial patterns caused by gaps in the measurements. Astronomers therefore use deconvolution methods to separate likely real structures from features introduced by the instrument. One widely used technique in radio astronomy is the clean algorithm, developed by Jan Hugbohm. The method begins by identifying bright points in the initial imperfect image. It then subtracts the known response that the telescope would produce around each point. This process is repeated many times, leaving a collection of model components that are combined with a smoother representation of the telescope's resolution. The result is not a casual digital touch-up. It is a controlled mathematical attempt to estimate the sky brightness most consistent with the measured data. Before reconstruction can be trusted, observations must be calibrated. Every detector produces some noise. Electronic components generate fluctuations. A telescope's sensitivity may change with temperature or time. Earth's atmosphere can absorb, scatter, or distort incoming radiation. Nearby transmitters may interfere with radio measurements. Astronomers observe calibration sources whose brightness or spectral properties are already well understood. These references help correct the instrument's response and place the data onto a meaningful scale. Background signals must also be measured and removed. An infrared telescope may detect heat from its own structure. An X-ray detector may record charged particles that are not part of the astronomical source. A radio telescope may receive emission from the atmosphere, the ground, or human technology. The corrections can be complicated, particularly when the desired signal is extremely faint. X-ray and gamma-ray detectors often treat photons individually. Each photon may be assigned an arrival position, an energy estimate, and a time. Scientists can then separate the events into energy bands. Lower energy X-rays may trace one temperature of gas, while higher energy X-rays reveal a hotter region or a different emission process. Spectral lines from iron, oxygen, silicon, or other elements can be isolated and mapped across a supernova remnant or galaxy cluster. The final image may assign a different visible color to each measured energy range. This allows one picture to display several physical conditions at once. When individual sources are too faint to detect clearly, researchers may use data stacking. They align observations of many similar objects and combine them. Random noise tends to average out, while a weak signal shared by the objects accumulates. A single distant galaxy may produce too few X-ray photons to stand out. Thousands of galaxies combined can reveal their average high-energy emission. Stacking sacrifices information about individual objects, but it can expose statistical patterns hidden beneath the noise. Astronomical data are also shaped by time. Time-domain astronomy studies how objects change in brightness, color, spectrum, or position. A static image may show where a source is located. A sequence of observations may reveal what the source is doing. Variable stars pulse. Asteroids move. Supernovae appear and fade. Active galactic nuclei flicker as matter falls towards supermassive black holes. Some changes unfold over years, others occur in seconds. Modern surveys repeatedly image large regions of the sky and compare new observations with earlier ones. Algorithms search for differences. They may identify a new point of light, a sudden brightening, an object moving against the background stars, or a signal with an unusual spectrum. Automated systems can distribute alerts within seconds or minutes, allowing other observatories to respond while the event is still active. Human researchers remain essential. A possible transient may be a genuine explosion, but it may also be a cosmic ray striking the detector, a reflection inside the telescope, a defective pixel, or an error in image alignment. Scientists examine instrumental artifacts, statistical significance, and alternative explanations before announcing a discovery. A computer can find something unusual very quickly. Deciding what that unusual thing actually means tends to require more patience. Computer simulations provide another important tool. Researchers simulate stars, galaxies, black hole accretion disks, supernova remnants, and the growth of large-scale cosmic structure. The simulation begins with physical equations and chosen initial conditions. It then calculates how the system may evolve. Scientists can produce synthetic observations from the result and compare them with real measurements. A simulated galaxy cluster might be processed as though it were observed by an X-ray telescope. A model black hole image may be blurred to match the resolution of a radio interferometer. This helps test whether a theoretical model can reproduce the structures seen in actual data. A simulation must not be confused with an observation. One represents what a set of physical assumptions predicts. The other records what an instrument measured from the universe. Clear scientific communication distinguishes between them. It also documents uncertainty. Every image has limits set by sensitivity, resolution, calibration, and processing choices. A faint feature may lie near the detection threshold. Two nearby sources may blur together. Missing spatial frequencies may hide very broad structures. Public images often compress a complicated chain of observation and analysis into one striking frame. For that reason, researchers record which wavelengths were used, how colours were assigned, what corrections were applied, and how confident they are in the features shown. Turning invisible signals into images is not simply decorative colouring. It is the rigorous translation of measured radiation into a form the human visual system can examine. The colours may be selected, but the structures beneath them are constrained by data. Through that careful translation, eyes designed for a narrow band of visible light can study radio jets, infrared dust, ultraviolet stars, X-ray plasma, and gamma-ray explosions. The image is not the raw universe. It is a scientifically constructed window into information that vision alone could never receive. The invisible universe is not hidden in only one way. Some parts remain unseen because their radiation lies beyond the narrow range detected by human eyes. Radio waves, infrared radiation, ultraviolet light, X-rays and gamma rays may cross the sky without producing any sensation of colour or brightness. Other cosmic messengers are invisible because they barely interact with matter. Neutrinos can pass through stars, planets, and detectors with little chance of leaving a trace. Dark matter is known primarily through gravity rather than light. Black holes conceal regions behind event horizons. Dust obscures distant stars, while cosmic expansion stretches ancient radiation beyond visible wavelengths. Distance itself creates another boundary. Light travels at a finite speed, so astronomy always observes the past. Some events are simply too faint, too remote, or too heavily concealed for present instruments to identify clearly. Scientific invisibility can therefore mean many things. It can describe radiation the eye cannot detect, particles that rarely collide, matter that appears not to interact electromagnetically, or information that remains beyond an observational horizon. Even when a signal exists, technology may not yet be sensitive enough to recover it. Every detector produces noise, electronics fluctuate, mirrors, antennas, and support structures emit or scatter radiation. Earth's atmosphere absorbs certain wavelengths and distorts others. The Milky Way itself creates foreground emission that can hide more distant signals. Dust, hot gas, charged particles, and nearby radio sources may all stand between an observatory and the faint object it is attempting to study. Sky coverage is also incomplete. Some telescopes examine only narrow regions at one time. Others can operate only during certain seasons or under suitable atmospheric conditions. A short-lived event may occur while the relevant instrument is facing elsewhere, undergoing maintenance or being asked to investigate something completely different. The universe does not arrange its explosions around a convenient observing schedule. New observatories are designed to reduce these limitations. The Square Kilometre Array Observatory will combine enormous numbers of radio antennas across sites in Australia and South Africa. Its name refers to the project's intended collecting scale rather than to one single solid dish. The observatory will study neutral hydrogen through the 21-centimetre radio line, allowing astronomers to map gas across the Milky Way and far beyond it. Measurements of hydrogen at great distances may help trace the formation of early cosmic structure, and the period when radiation from the first luminous objects rionized much of the hydrogen between galaxies. The Square Kilometre Array Observatory will also test gravity through precise pulsar timing, investigate cosmic magnetic fields, and search for transient radio signals. Its broad view and high sensitivity should make it particularly useful for discovering brief events that cannot be predicted in advance. Gravitational wave astronomy is also preparing for a new generation of instruments. The Einstein Telescope is a proposed underground European observatory designed to improve sensitivity across a wider range of gravitational wave frequencies. Cosmic Explorer is a proposed ground-based observatory in the United States, with arms much longer than those of current detectors. These instruments could observe black hole and neutron star mergers at far greater distances, detect weaker systems, and follow compact objects through more of their final approach. The Laser Interferometer space antenna will take gravitational wave detection into space. It is planned as a triangular formation of spacecraft separated by millions of kilometers and connected through laser measurements. Its enormous scale will make it sensitive to lower frequency waves than ground-based observatories can detect effectively. Possible sources include compact binary stars within the Milky Way, the mergers of massive black holes and smaller compact objects gradually falling into much larger black holes. Visible light surveys will contribute through repeated observation, rather than through one exceptionally deep picture. The Vera C. Rubin Observatory is designed to image large areas of the southern sky again and again through the legacy survey of space and time. By comparing new images with earlier ones, the survey can identify what has changed. Supernovae will appear and fade. Asteroids and comets will move against the background stars. Variable stars will pulse. Active galaxies will flicker as matter feeds their central black holes. This time domain approach turns the sky from a static map into a continuously changing scientific record. The European Space Agency's Euclid mission and the National Aeronautics and Space Administration's Nancy Grace Roman Space Telescope are intended to examine cosmic structure across enormous distances. Both will study large populations of galaxies and use gravitational lensing to trace matter that cannot be seen directly. They will also measure how galaxies are distributed across space and cosmic time, helping researchers investigate the expansion history of the universe. These observations may clarify whether dark energy behaves like a cosmological constant, or whether its influence has changed. Neutrino observatories are expanding as well. A planned enlargement of the IceCube Neutrino Observatory would increase its sensitivity to high-energy cosmic neutrinos and improve estimates of their arrival directions. In the Mediterranean Sea, the cubic kilometre neutrino telescope is being constructed as a network of detectors anchored deep underwater. The surrounding water provides a large, transparent volume in which rare neutrino interactions can produce detectable Cherenkov light. Together, neutrino facilities in different parts of Earth can improve sky coverage and help locate powerful accelerators such as blazars, stellar explosions, and tidal disruption events. Some of the deepest mysteries remain stubbornly unresolved. Dark matter has been inferred through galaxy rotation, gravitational lensing, cluster dynamics, and cosmological structure, yet its physical identity remains unknown. Underground detectors have searched for rare collisions with atomic nuclei. Particle accelerators have looked for missing energy that might indicate the production of unseen particles. Gamma-ray and neutrino observatories have searched for possible products of dark matter annihilation or decay. A null result is not an empty result. When an experiment finds no convincing signal, it can exclude particular particle masses, interaction strengths, or theoretical models. The possible landscape becomes smaller. Dark energy presents an even broader uncertainty. It may be a cosmological constant, meaning an approximately constant energy density associated with empty space. It may involve a dynamic field that evolves over time. Accelerated expansion could indicate that gravity behaves differently across cosmological distances, or that assumptions built into the standard cosmological model require revision. Several possibilities can reproduce parts of the existing evidence. The difficulty lies in finding observations precise enough to distinguish among them. Even ordinary matter has managed to hide surprisingly well. For years, measurements of the early universe indicated that more baryonic matter should exist than astronomers could account for in stars, galaxies, and easily observed gas. This became known as the missing baryon problem. Much of the missing material appears to be distributed as extremely thin, warm, or hot gas between galaxies and along the filaments of the cosmic web. Because the gas is diffuse, it emits only faintly. Astronomers study it through ultraviolet absorption, X-ray observations and signals produced when cosmic microwave background photons pass through hot electrons. The matter was not exotic. It was simply spread so thinly that finding it required the universe to be examined in less obvious ways. Fast radio bursts provide another reminder that discovery is not finished. These brief pulses of radio emission may last only milliseconds, yet they can release extraordinary amounts of energy. Some repeat. Others have been detected only once. Several have been localized to distant galaxies, and at least some repeating activity has been connected with highly magnetized neutron stars. Their full range of sources and mechanisms remains under investigation. Fast radio bursts also pass through intergalactic plasma, which disperses different radio frequencies by different amounts. This makes them useful probes of otherwise difficult to detect matter between galaxies. Invisible wavelengths may eventually reveal the first generations of cosmic objects. The first stars formed from gas containing almost no elements, heavier than hydrogen and helium. Their ultraviolet radiation began changing the surrounding universe by ionizing neutral hydrogen. The first galaxies gathered around early concentrations of dark matter. Seed black holes grew through accretion and mergers, with some becoming surprisingly massive within the first fraction of cosmic history. Radio observations of neutral hydrogen, infrared studies of highly redshifted galaxies, and X-ray searches for early black holes may help reconstruct this hidden era. There may also be messengers that have not yet become part of astronomy. Before radio astronomy, the radio sky was physically present, but observationally unexplored. Before neutrino detectors, the interiors of stars communicated through particles that passed unnoticed through Earth. Before gravitational wave observatories, merging black holes disturbed space-time without producing a signal humans could measure. Future science may discover another form of information or learn to detect a phenomenon currently buried beneath noise. Scientific invisibility is rarely absolute. Something that cannot be seen directly may still alter motion. It may heat nearby matter, delay arriving signals, rotate polarization, bend light, or disturb space-time. An unseen object can reveal itself through the behavior of everything around it. The invisible universe is therefore not a small addition placed around the edges of the familiar sky. It is the larger physical reality. Visible astronomy offers one narrow and beautiful sample of that reality, shaped by the limited sensitivity of human eyes. Beyond it lies cold gas, energetic plasma, hidden particles, curved space-time, unknown matter, and the changing expansion of the cosmos. The universe has never been silent or empty. Much of it has simply been speaking in ways we are still learning to hear. The invisible universe is not a distant region concealed somewhere behind the visible sky. It is the full cosmos, revealed through signals that human eyes cannot detect. Visible light occupies only a narrow part of the electromagnetic spectrum. Beyond it, radio waves trace cold hydrogen and immense galactic jets. Microwaves carry the oldest light we can observe, released when the young universe first became transparent. Infrared radiation reveals warm dust, hidden stellar nurseries and distant galaxies, whose light has been stretched by cosmic expansion. Ultraviolet observations expose hot young stars, ionized gas and energetic stellar atmospheres. X-rays reveal million-degree plasma, accretion disks, neutron stars and matter heated near black holes. Gamma rays identify radioactive decay, extreme particle acceleration, and some of the most powerful explosions known. Light, however, is only part of the story. Cosmic rays carry atomic nuclei and other charged particles from energetic environments, although magnetic fields twist their paths before they reach us. Neutrinos travel through dense matter almost undisturbed, bringing information from the cores of stars, supernova, and distant cosmic accelerators. Gravitational waves carry no light and no particles. They are moving distortions in space-time itself, produced when massive objects such as black holes and neutron stars accelerate and collide. Dark matter is different again. It is inferred through gravity, through the motion of stars, the structure of galaxies, and the bending of distant light. Dark energy should not be confused with it. Dark matter helps bind galaxies and supports the growth of cosmic structure. Dark energy is associated with the accelerating expansion of space across the largest distances. Much of invisible astronomy therefore depends on inference. Yet this does not make it uncertain guesswork. Almost all science relies on measurable effects. We understand wind by watching what it moves. We study atoms through the light they absorb and emit. Even an ordinary visible object is known because photons interact with it and reach our eyes. Scientific instruments extend that process. Radio antennas, cooled infrared detectors, X-ray satellites, neutrino observatories and laser interferometers allow human beings to receive forms of information that biology alone would miss. These instruments do not replace reasoning. Their signals must be calibrated. Noise must be removed, uncertainty must be measured, and important results must be tested through independent observations. Multi-messenger astronomy brings those careful measurements together. Light may reveal temperature and composition. Neutrinos may escape from a hidden interior. Gravitational waves may reveal the masses and motion of compact objects. Combined, these messengers can reconstruct a single event with far greater clarity than any one signal could provide. If humanity trusted only unaided vision, the universe would appear far emptier than it truly is. We would miss cold gas between stars, dust glowing in infrared light, hot plasma filling galaxy clusters, magnetic fields guiding charged particles, neutrinos crossing entire planets, and black holes revealing themselves through gravity. The night sky is never truly silent or dark. Information is constantly moving through it in forms too faint, too energetic, too weakly interacting, or simply too unfamiliar for the human body to notice. Astronomy is the patient art of learning how to receive those messages. With each new instrument, the darkness becomes more detailed. With each careful measurement, the invisible universe becomes a little easier to understand.